remind you to turn on your camera and use the virtual background that's available in the comment box. We will take picture for documentation of this event, and I will be driving. To take a picture, we start from slide 1, 3, 2, 1. Okay, next slide. 3, 2, 1. Okay, for the last one, 3, 2, 1. Okay, thank you everyone. Without further ado, let us now start our program, who will be guided by Dr. Lucy Ernawati as our moderator of this event. Please welcome Dr. Lucy.
Okay, thank you, Miss Rizka. Honorable all the guest speakers, ladies and gentlemen, a very warm greeting to each and every one of you. As introduced earlier by the Master of Ceremony, my name is Lucy. I'm serving as moderator for today's meeting. First of all, I would like to thank to all the audience. Thank you for joining us in the last guest lecture session in our events. Today we have gathered here to discuss the topic of renewable material energy engineering for energy and environmental application. We are very proud to announce that this program is being conducted along with the supporting under Ministry to Education and Culture of Republic Indonesia in conjunction with the Education Endowment Fund Investment LPDB. The greatest appreciations toward to all the guest speakers attending today's meeting, Prof. Jaka Sunarso from Swinburne University of Technology as our invited world-class professor, Dr. Ruri Agung Wahyuwono from Department of Engineering Physics, Institut Teknologi 10 November, Surabaya, Dr. Wibawa Hendra Saputra from Department of Chemical Engineering, Institut Teknologi Bandung, and our last speakers, Dr. Hairus Abdullah from Universitas Prima Indonesia. And now Dr. Hairus Abdullah is visiting postdoctoral fellow in Department of Material Science and Engineering, National Taiwan University of Science and Technology. Well, it is fundamental to search for alternative material sources that are renewable and to find new ways of using energy more efficiently. Any such new technology will most likely rely on new material with outstanding functional properties. In this guest lecture session, we will elaborate the development of renewable materials and learn how the advanced material play important role for sustainable energy and environment from the perspective of an experience from our invited speakers. Well, without any further ado, I would like to invite Prof. Jaka Sunarso from Swinburne University of Technology as our first presenter. Prof. Jaka will deliver the presentation with the topics research study on co-doped perovskite for solid oxide fuel cell cathodes. Prof. Jaka, the time is yours. Okay, we will wait Prof. Jaka to deliver the presentation. Hello, Prof. Jaka, are you ready? Hello, Prof. Jaka. Wait for 5 minutes. Prof. Jaka will join in 1 minute. Because today Prof. Jaka also has the others conference, and he also invited as speakers in others conference. So he needs to fix all the times to deliver the presentation into meeting. So please wait 1 minute later, he will join. Okay, hello, Prof. Jaka. Good morning, Prof. Jaka.
Hi, good morning, Lucy.
Okay.
Good morning, Rizka. Hi, Rose, with Hendra.
Good morning, Pak Jika.
Right. Sorry, I have another things going on also at the same time, so I just managed to join today. Just now, sorry. So now it's my turn to share my screen, right?
Yes, Prof.
Okay.
Time is yours.
Sure. So everybody can see my screen.
Yes, we can see it's clear, Prof.
Okay. Okay, then thank you. I think everybody for having me today. So my talk today in this third sessions of the world-class professor today will be a little bit topic on my research. This is the past research on the solid oxide fuel cell cathodes, because this topic match the bigger theme that we bring in this particular sessions. Okay, so wait a second. I try to. So a little bit about me. I think I get my first degree from ITS Surabaya, then my master and PhD from Queensland. I joined Swinburne University of Technology in 2016. And my PhD, my research was on the oxygen ionic transport membrane using a perovskite materials. In my first postdoc and my second postdoc, my research moved into electrolyte, ionic liquid electrolyte for lithium batteries. And then I started my academic career a bit late, which is 2016, because you all know that postdoc is contract-based positions, right? I mean, then I think in 2019, I was promoted as an associate professor, and started this year, I promoted as a professor. Okay. I'm quite active also as an editor for several journals. So the one that I have assigned a lot, I handled a lot, is an assignment from the process safety and environmental protection. They normally send me, the journal manager normally send me to handle a paper when it's about the biomass conversion. And then it's about the waste management resources and a little bit on the modeling side of that thing as well. I'm also involved as a guest editor for the carbon resources conversion. This one is a KI Elsevier journal. So the share is coming mostly from the China publisher, but the host is Elsevier. So all this article is published in Science Direct. And also the resources, chemicals, and materials, I'm also enrolled. I'm also involved as an editorial board member. I'm also an associate editor for the Asia Pacific Journal of Chemical Engineering, and also editorial board member for MDPI Membranes open access journals. So in today's sessions, I will overview a little bit on the three different co-dope materials. When I talk about the co-dope materials, meaning that we put in two different dopants into the perovskite lattice. So in the first component is the SSNF, which is the dual doping will be the scandium and the niobium. And the second one is the niobium with the tantalum. And then the third one is the scandium and the tantalum. So I'm going to talk a little bit into the SSNF, SNTFX, and SSTFX. The other things beside the similarity, or what basically the integral aspects from these three materials, beside the co-dope, meaning co-dope is we put in two different dopants into the B side. In here is also, as you can see, that in the B side we only have the iron, so there is no cobalt at all in the perovskite lattice. So our group and collaborators, they depart away from the cobalt, because cobalt is more easily to be thermally reduced at high temperature. Of course, in terms of the area-specific resistance and the performance in solid oxide fuel cell, then if your perovskite contain cobalt, then you expect that the electrochemical performance will be higher, but at the same time that will be traded off by your stability. So meaning you if you consider about the lifetime performance, then the one that contains cobalt the performance will be reduced more quickly compared to the one without cobalt. Okay, so the first one will be the topic is we published this one in the Energy Journal. It's I was doing my postdoc in University of Waterloo, and it involves several collaborators from Nanjing University and also from Taichung and also from China Jiliang University. Okay, so as in all the research structure for the cathode for solid oxide fuel cell, normally we would like to know what is the crystal structure for these particular materials. So these particular materials, the crystal structure, how we do these things is we involve or we ask an electron microscopic to do a selected area electron diffraction pattern, high resolution TEM image, and then also complemented by the powder X-ray diffraction pattern. Okay, so based on the SAED pattern, which is done in along the axis of 110 in here, and then also on the HRTM image, we can get the lattice spacings for this particular 0.78 in here for the for the plane of 001, and then we are able to conclude that this particular structure has a tetragonal lattice with the space group of P4MMM, okay, where we have an A of 3.912 with the C of 7.794. So this is not a cubic structure. It's basically because we have something that are a bit longer in the other directions with respect to the one in the other directions. So this one we have the tetragonal perovskite lattice. And then the next thing that we want to check is the oxygen non-stoichiometry in here, because as you know, in the structure in here you have this oxygen vacancies. So meaning that if oxygen in here is supposed to have a charge of 2-. So if your if everything in here has an exact cation charge of 6, then we will not have an oxygen vacancies in here. But the meaning in here is because 3- this particular oxygen non-stoichiometry. So meaning that oxygen non-stoichiometry is the one that that helps for the transport within your perovskite lattices. So that's that we need to check whether this oxygen non-stoichiometry, what is the variations at a different temperature. So as we go from 400 to 1000, we can see that the oxygen non-stoichiometry in here increase from 0.2 to 0.45, and this one is related with the reductions of the iron oxide in the perovskite lattice in the B side. So as the oxygen non-stoichiometry increase from 0.2 to 0.45, actually the oxidation state for the iron in the B side reduced from 3.7 to 3.0. Okay, so that is very important because the performance of the perovskite, the oxygen deficient perovskite is normally can be correlated with the oxygen non-stoichiometry in the perovskite. And then the next one that we want to check is also the electronic conductivity, the electrical conductivity or the electronic conductivity. So the electrical conductivity in here is the sum of the oxygen ionic conductivity with the electronic conductivity. And the electronic conductivity generally in perovskite that contains a transition metal ion is much higher than the oxygen ionic conductivity. So we can safely say that the electrical conductivity in perovskite reflects the electronic conductivity of a perovskite. So we have two different reagents with an inflection point at 500 degrees Celsius. And the inflection is ascribed with the reductions of the Fa4+ to Fa3+. when we heat it from 400 to 1000 degrees Celsius. I have not gone into explaining what is the solid oxide fuel cell, but the solid oxide fuel cell is normally a type of the fuel cell that are operated at the high temperature. It's a bit different with the polymer electrolyte membrane fuel cell. So polymer electrolyte membrane fuel cell, you have several different types. The conventional one is the one that you operate at room temperature. And you also have a higher than ambient temperature polymer electrolyte membrane fuel cell. But solid oxide fuel cell is a special type of the fuel cell that people operate at, I think, normally above 400 degrees Celsius. Okay, so then I continue into the thermal expansion behavior using dilatometry. So you know that as we are involved with the heating at the high temperature, then we need to be careful with the expansion component of our cathode as well. So we need to check what are the thermal expansion coefficient of this cathode material. So we subjected this material to the dilatometry, and we find that there are two different regimes of the expansion. The first one is below 450, and the other one is above 450. As you can see, the slope is quite different at these two different regimes, right? And if we talk about the overall TEC, then that will be 16.2 10 minus 6. And of course, these TEC values are lower compared to the cobalt perovskite oxides because, like I told you again, the performance of the cathode component is tightly related with the stability. So if you have a lower thermal expansion coefficient, then you will have a lower expansions as you heat up, and that will affect the mechanical integrity of your solid oxide fuel cell. Okay, so this one is the figures into the symmetric cell. So we make the symmetric cells in order for us to be able to characterize the area specific resistance. So in solid oxide fuel cell, normally if we want to test it, we want to test the cathode performance, what we did is we make a symmetrical cells in here and we check the area specific resistance as a function of temperature. In the beginning, when we do these things using a spray coating, we find that everything is well integrated to each other. You can see the interface is quite well. Okay, so there is no defects. So there is a thermal compatibility between SSNF and SDC. Okay, now we also check again using the powder X-ray diffraction pattern. Three different. Mainly, we focus on the SSNF with the SDC mixture in here because we would like to know if there is any additional phase that were formed after we combine this SSNF with the SDC mixture and heat it up to 1000 degrees Celsius. Okay, if we have an extra peaks that come out that cannot be indexed with respect to the individual components, which is the SSNF and the SDC, that means that we have a new phase form, which can come from the reactions between the components of the SSNF and the SDC. So in here, we don't see anything because all the peaks that come up from the mixture of the SSNF and the SDC that were heated up to 1000 degrees Celsius can be indexed with respect to the peaks of the SSNF and the SDC. So meaning that our mixture is quite stable when we heat it up to 1000 degrees Celsius. And this shows the next one is showing you the characterizations for the symmetrical cells for the different cathodes. Okay, so in here you can see that as the temperature is increased, then the semi-arc circles size becomes smaller. So this one is at 650, this one is at 700 and 750. Because you know that when you increase the temperature, meaning you are making the diffusion process for the ions and the electronics becomes much easier. As a result, you reduce the resistance for the cathode. Okay, and then as you can see that if you decrease the temperature even lower than 650, which is 600 degrees Celsius, and 550 degrees Celsius in here, then the arc size in here becomes higher. Okay, so what we can conclude, or what we can say in here is that the ASR for this particular cells is 0.021 at 750 and up to 0.821 at 550 degrees Celsius. The other thing that are interesting is the activation energy. So the apparent activation energy that we have from this for this particular cathode will be 127.5 kilojoule per mole, which is much lower than the S and F cathode. So this means that in the S and F cathode, we are only doping with one dopant, which is the niobium. So when we change that also with the scandium, when we added a scandium into this B site, or what we say if we introduce a double dopant into the B site, we can reduce the activation energy. The activation energy in here implies the thermal activation nature of a particular material. So generally, if you have a very high activation energy, meaning that you have you basically have a huge effect for the same increment of the temperature that your system face. So with the respects of the stability and the better performance, normally solid fuel cell scientists will want to have a lower activation energy altogether with the area specific resistance. Okay, that will be the first material. The second material is we move into the SNTF in here. So we are doping with the niobium with the tantalum on the B side, while we are keeping the iron at 0.8. This one is in collaborations with my with the wife of my friend, my long-term collaborator in here. At the time, she were at Nanjing University of Aeronautical, I think, if not wrong. Okay, so we would like to check the effect of the doping. So as we basically replace the tantalum with the niobium, so you can see that in here tantalum 0.2. So in here we replace 0.05 of tantalum with niobium. In here we replace 0.1 tantalum with niobium. In here we replace 0.15 of the tantalum with the niobium. And then we go to the other extreme where we basically replaces all the tantalum with the niobium. We can see that all of them corresponds to the PM3M space group. Of course, I would have to say that we ignore a little bit of the impurities phase that are formed in here, as you can see a little bit in here. So we only focus on the big picture of this powder X-ray diffraction pattern. Okay, the weak peak at 34 degrees Celsius can be attributed to the lattice ordering, and then the weak peak at this 29.6 is associated with the copper K beta radiation. So in this particular XRD, we don't use a copper K alpha, but we use a copper K beta. Or no, we are using copper K alpha, but it was not very pure, so there is still a little bit of the copper K beta radiation that that manifests in the system. Okay, then we check the next one is the temperature dependent electrical conductivities. You can see that we check it as we heat it up from 300 to 900. So we capture two different behaviors in here. The first one is the electrical conductivity increase with temperature up to around 500, and then followed by the decrease in the electrical conductivity from 500 to 900. So this can be correlated with the semiconductor behavior and metallic behavior. So in metallic behavior, if your material has a metallic behavior, meaning that the electrical conductivity reduced with increasing temperature. If your material exhibits a semiconductor behavior, then it's increased with increasing temperatures. Okay, we can see that the highest electrical conductivity is obtained when we put equal amount of the niobium and tantalum into the B sides of the perovskites in here, which is exhibited by x equals 0.1. Then we check again the thermal expansion behavior. As you can see, the thermal expansion behavior are not very far away from each other, considering the small increment of this delta L divided by the L naught in here. Okay, which means that the variations in here, as we can see, this one, the last column in here shows the overall thermal expansion coefficients. It's not very far away from each other, so it varies a little bit from 13.5 to 15.11 when we raise to 10 to 6. Okay, what we call in here a PIT is the point of the inflection temperature. Okay, as you can see that when we start on adding more of the tantalum, I think tantalum or niobium, I think the X in here is correspond to the tantalum. So as we increase the amount of the tantalum, then our thermal expansion coefficient increases as well, meaning that we will have a higher thermal expansion coefficients because each of the different cation, which is tantalum and niobium, they have a different ionic radius. This shows the interface between the SNTF 0.1 with the SDC electrolyte. Okay, so we see that there is no problem after we sinter the fuel cell components. After we attach the STNF cathode into the SDC electrolyte. Okay. Then we also do what we did again. We mix the powder STNF with the SDC, and we increase it up to 1000 degrees Celsius. We subject to 1000 degrees Celsius. We find that there is no extra peaks that come out. Okay, so meaning that our materials are quite stable. Next, we do also the symmetrical cell test. Okay, we can see that the area specific resistance is varies from 0.046 to 1.990 at 550 degrees Celsius. And this one is basically showing the comparisons for all the dopant components. So imagine that we are making 5 different symmetrical cells, and we tested it one by one. And we also make another, the one that we did in here is what we call a symmetrical cell. The one that we call in here is a full cell. Full cell meaning that we put in the electrolyte, we attach a cathode, and we attach an anode. And then we put in the hydrogen into the anode side, and then we expose the cathode side to the air, and then we start the polarization experiments. Okay, we carry out from 600 to 800 degrees Celsius, and we find that the maximum power density increased from 622 at 600 degrees Celsius to 1900 at 800 degrees Celsius, which is quite good. And these are the SEM on the structure of the full cell in here. So we can see that the anode side, they have a very how to say that thing? It's a well-tailored structure, meaning that it has a progressively different structure. So this IJPACE is used as a current collector, and then this STNF is used as the porous cathode layer, and then we have another layer which is the SDC in here, which is coupled with the YIZ in here. Okay, and then NIYIZ in here. Where if you ask me why we are using this kind of structure is because we want to ensure that there is no leaking of the ionic, because sometimes as SDC in here, although we categorize as an ionic conductor, if this is exposed to the reducing atmosphere, which is the hydrogen, then it may have a little bit of the electronic conductivity. Okay, so with this kind of structure, then we ensure that everything, that there is no leaking of the ion into from the cathode to the anode side. Okay, so the next one, the next material that we invented it with our collaborator is SSTF. Okay, so in here we are using a scandium, and this one is on collaborations with big professors in Curtin University, with Nanjing University of Technology, and the Hong Kong Polytechnic University. The first thing that we did is we compare the structure of the co-dope one. In this particular scenario, we only interested with the one that we dope, where the tantalum is only 0.0025, the scandium is 0.0075. We compare it with where only scandium exists at 0.1 on the B side, and on the TA of 0.1 on the B side. So as STF 75 in here shows the lowest ASR of 0.092 at 600 degrees Celsius. Okay, what are the other conclusions that we can take in here is except for SSF, the other sample shows a weak peak before 20 degrees Celsius, which come from the Orville-Brown-Miller phase, and all the peaks in here basically can be indexed according to the primitive perovskite structure with a space group of 2 to 1. This one is showing the SEM EDX, so meaning that all the components exist homogeneously, they are distributed homogeneously, and they are present in very uniform distributions all over the SSTF 75 sample that we have in here. With respect to the HRTM and the selected area electron diffraction in here, we cross-check whether XRD shows us that it is a PM3M structure. So in here we want to check as well whether the HRTM and the SAED shows that this is a primitive cubic perovskite structure, and they did. Okay, so we basically confirm. And then we do a high temperature XRD pattern of the SSTF when during heating and cooling at 10 volume % of the CO2, because this material is quite special. So we intend to use this in the single chamber solid oxide fuel cell. So when I talk about the single chamber solid oxide fuel cell, you don't differentiate the chamber between the cathode and the anode, meaning that you operate the whole solid oxide fuel cell within one environment that contains the hydrogen, contains oxygen. So it's basically the solid oxide fuel cell will be exposed to reducing and deoxidizing gases at the same time, basically. And we can see that there are impurities that are formed at when you are heating up to 500, but disappear when you cool down. And the essential findings in here is that SSTF 75 structure is stable in both air and CO2 atmospheres. Okay, and then we do what we did in the previous slides as well. We basically check after we sinter this SSTF 75 with the STC, whether they are stable, whether there are no evidence of the phase impurities that perform in the systems, and yeah, we did get a good result, which means that we don't find any peak impurities that comes out after we mix up the two powders, the electrolyte with the cathode, and we heat it up to high temperature. And in here we then check the SSR at the different temperature again, and for a different dopant component as well. Okay, so we find that the best compositions in here give us ASR of 0.039 at 650 and 0.25 at 550 degrees Celsius. So this component is actually performing much better than the other two cathodes that I showed in the previous two different set of slides. Okay, and then when we compare this with the other materials as well, as we can see in here, then our material SSTF in here is located not too bad. It's located at the lower end of the ASR, which means that the only other cathode compositions that can beat this particular composition is only BSCF and SSNC. And BSCF are basically the benchmark cathode for solid oxide fuel cell, is the best material. SSNC also we developed with our with my best friend and collaborators back in 2013. We published that finding in the Angewandde Chemie. Okay, so yeah, this one is one of the best material, and SSNC contains a cobalt and BSCF containing a cobalt. This material is free from cobalt, so this is a very standing out advantage that this cathode have. Okay, then we check again the now the emphasis is on the stability. Okay, so we subjected the symmetrical cells to 10% of volume of the CO2. Okay, we check in air how much after we expose CO2, then we remove CO2, what is the performance. So you can see that there is an increase a little bit. If BSCF, then the increase is very apparent. For the SSTF75, the value is the same. And for the SSTF75 SDC, then there is a little bit of increase in here. And this shows a little bit of, this shows the composite cathode, what happens after they are exposed to 1% CO2, 5% CO2, 10% CO2, and then after the CO2 is completely removed compared to the beginning. So we start from here, the area specific resistance. As we expose 1% CO2, the area specific resistance increase. 5% CO2, the area specific resistance increase, then 10% CO2 is increased because obviously when you put in a CO2, then the CO2 will be absorbed in the surface of your cathode, and that will basically block the reactions of your oxygen reduction reactions in the surface of your cathode. But as the CO2 is removed, then you can recover about the same performance with your original performance, which means that although the absorption happens, but the CO2 does not react with your materials, which means that your material is very stable. Okay. Then I think the slides in here is basically just showing the explanations into why when you dope scandium with the tantalum, you get a much better performance than if you only dope with one dopant, which is the scandium or the tantalum. And basically that's what is shown in here is basically they do a density functional theory calculations. As you can see in here, the crystal cell energy, if you put in the two dopants, is in between. Okay, but this formation energy of oxygen vacancies will be a bit different. So the SC doping is basically increasing the oxygen vacancy concentrations, and the TA doping is increasing the perovskite acidity and average metal oxygen bond energy, which is contributing to a better CO2 resistance. Because CO2 is an acid component. So if your perovskite is a basic component, then there is a tendency between the acid and basic to react. So if you reduce the basicity of your perovskite, meaning you increasing the CO2 resistance of your perovskite. And next thing that we did is we make a full cell, okay, with the same configurations again, like the one that we showed in the previous, in the second set of slides. We managed to get 550 to 180 milliwatt per centimeter square as we play with the CH4 to oxygen ratios in here. So this solid oxide fuel cell is a bit special in that we don't operate it using a hydrogen, but we use a methane. Okay, because obviously it will be more expensive to fuel a fuel cell using a hydrogen than if you fuel a fuel cell using methane, because methane is more abundantly available. Whereas if hydrogen, then you need to get it produced by electricity or using a steam methane reforming of methane. Okay, then we pick up one ratio of the CH4 with the O2, and we probe it again. We see that we see that there is a bit of reductions in the OCV from 0.93 to 0.9. This is due to the increasing temperature and reduced cathode selectivity for oxygen reduction reaction due to enhanced methane oxidation catalytic activity and the cathode surface at higher temperatures. This one in here is showing the test as a temperature as a time. So when we increase the time up to 5,000 minutes in here, and we compare between the BSCF with the SSTF, we see that the BSCF decrease, but the SSTF, the performance, although it fluctuates a little bit, but they maintain a much more stable performance in here. Okay, and the instability in here is caused for the BSCF case is caused by the reactions between the BSCF and the CO2. So in conclusion, we have discussed 3 different materials. Okay, and the best compositions for the second components in here will be this SNTF 0.1. And the best compositions for the third family of the compositions in here will be the SSTF 2.5. The lowest ASR is basically obtained by, well, the temperature is a bit different, but I would say that the best cathode components among these 3 is this one, the SSTF 25. Okay, and then we have tested the ASR and the symmetrical cell configurations. So the key message that I can tell in here is that research is very dynamic. It will move, and something that we find from 10 years ago will not be in par with what you find now. And research is very mobile, meaning that what people are working at very hard to keep on increasing the practical applicability of the solid oxide fuel cell technology. And perovskite is one of the versatile materials that can be used for many different applications. One of them is the solid oxide fuel cell cathode. I would like to take this chance to thank my collaborators in China, particularly because of their because of the opportunity for them to involve me in their work, and the collaboration has been ongoing far away since the time of my PhD in Queensland up to now. Even though I don't really do my solid oxide fuel cell cathode experiments in Swingben, Sarawak, but they always welcome me to their lab and they always involve me in their work as well. And finally, I am happy to welcome collaborations with all other peoples in this particular area or in any other areas that you would like to collaborate with me. Thank you so much for having me to talk for these particular sessions.
Okay, thank you, Prof. Jaka, for the presentation, which relates the perovskite for solid oxide fuel cells cathodes. And these materials can provide an alternative and efficient options to conventional electricity production device, as I understand. And it is very informative and nice research. Well, before we are going to the next presentation, I would like to remind to all the participants, we will have discussion session, questions and answer after all the presentation from the guest speakers finished today. And for the participants who wants to ask some questions, can write it directly in chat column or raise hand by opening your microphone. And now we are going to the next presentation that will be delivered by Dr. Renat Ruri Agung Wahyono, commonly addressed with Dr. Ruri. Dr. Ruri will deliver the presentation with the topics photocathodes optimization for solar energy conversion. Dr. Ruri, are you ready? Dr. Ruri?
Yes.
Okay.
Lucy, is my voice clear?
All right. Time is yours, Dr. Ruri.
Okay. Let me. Okay, good morning, everyone. Thanks, Bu Lucy, for inviting me to deliver talk in this world-class professor lecture series, and also salam kenal Pak Jaka, Pak Wibawa Hendra, dan Pak Hairus. So I am Rudi Wahyono. I'm from Department of Engineering Physics, ITS Surabaya, and in this occasion, I would like to present my talk entitled "A Photocathodes Optimizations for Solar Energy Conversion Device." Particularly, I will discuss the development of dye-sensitized photocathodes for photoelectrochemical cells. And we will discuss the photo-induced charge transport dynamics at the dye-semiconductor interface. So in principle, the talk comprises of the introductions, which motivates this work and shows challenges in dye-sensitized electrode-based solar energy conversion devices, and then the methodology that I will briefly explain later, and some results which covers the optimizations of electrode materials and photocathodes interface. So, as we might already know, that solar energy renders green and renewable energy source with massive power up to 100,000 terawatts, which can fuel the whole world energy demand. And therefore, solar energy conversion technology, especially solar cells, has emerged up to now. And as we see in the solar cells chart efficiency in the right panel here, one of the promising technologies is solar cells based on the sensitized electrode, which is called dye-sensitized solar cells. Although the current development is almost saturated, but this technology has several advantages over the conventional silicon solar cells, such as the low-cost fabrications, high performance under diffuse radiations, and high stability under high temperature. And furthermore, we also note tandem dye-sensitized solar cells that combine the N-type and also P-type dye-sensitized solar cells that should be able to break the Schottky-Quisha limit. But unfortunately, the very low performance of the currently P-type dye-sensitized solar cells limits the current efficiency of tandem solar cells. And therefore, in this talk, we try to discuss the optimizations way to the current performance of P-type dye-sensitized solar cells. So the working principle of the P-type dye-sensitized solar cell is basically illustrated in this animations. So the solar cells consist of dye-sensitized nickel oxide as a working electrode, and also iodine-based electrolyte as redox mediators, and also platinum-coated conductive glass as the counter electrode. And then upon irradiations, the dye is excited and followed by hole injections from the excited dye to the valence band of the nickel oxide, and then subsequently the reduced dye is regenerated by the triiodide and redox mediator regenerations occurs, yielding an external current flow. But it should be noted that there are recombinations reactions that limits the net current generations within the solar cells. This involves injected holes and also surface strip holes as geminate and also non-geminate recombination source. But we have also interfacial recombinations between the trap holes and also the electrolyte there. So from this point, it is essential for us to understand how the charge injection and recombination mechanisms to guide the optimizations route of the solar cells components, mainly the electrodes materials and also the dye. So concerning the electrode materials, challenges for optimizations includes developing materials with a high surface area and also the dye loading to generate high photocurrent, and then low defect concentrations to reduce recombinations reactions, and also appropriate redox properties to allow hole injections. So this is the three important aspects in material aspect. And regarding the dye sensitizer, the complex dye should have an appropriate excited and also ground state properties or ground state potentials for efficient charge injection. And also they should have a broad absorptions in the visible regime, because we want to harvest the solar irradiations, which mainly in the visible and also near infrared later. In this context, ruthenium complex or ruthenium polypyridyl complex are interesting, since the absorptions of this complex in the visible regime is broad and can be further optimized by tuning their ligand characteristics. But for P-type dye-sensitized solar cells, the organic push-pull dye is known as the best sensitizer at the moment. However, ruthenium sensitizer can also be optimized by ligand design, stabilizing the ligand-centered radical anion upon form upon the hole injections away from the nickel oxide surface. So, such as ruthenium complex with dipyridophenazines or DPPZ ligand should be DPPZ ancillary ligand. I would say it should be used as a benchmark ruthenium complex in this way, because the prevalent dye design is that the HOMO, the higher occupied molecular orbitals of the dye sensitizer should be localized on the anchoring group to overlap with the valence band orbitals of the nickel oxide, while the LUMO here, the lowest unoccupied molecular orbitals, extends to the distal periphery of the dye molecules away from the nickel oxide surface. So in this regard, adding linkers, for example, here, from G, which can extend the distal periphery from the dye molecules away to the nickel oxide surface, is one of the approach to optimize the dye design. So in these discussions today, we will restrain our discussions only on the evaluations of the structure properties and performance correlations of the metal oxide semiconductors and the optimizations of the dye sensitized nickel oxide interface by ligand design and applied bias. So here the methodology. So we have used nickel oxide as photocatalytic materials that were synthesized by means of wet chemical methods using different nickel source. So all material characterizations was done to assess physical, optical, microstructural, as well as electrochemical properties. And the ruthenium photosensitizer here, which is dipyridophenazine-based ruthenium complex, and all the catalyst was prepared by our collaboration partner from University of Ulm. So as the whole injections and also charge recombinations process occurs in a femtosecond to microsecond time scale, so we use ultra-fast time resolve or transient absorption spectroscopy. So in our pump probe setup, the dyes in solutions and also the dyes when it is immobilized on nickel oxide surface were excited at 480 nanometers at the metal to ligand charge transfer band of the dye and probe with the white light continuum. So in our setup, the pump beam is chopped just like this, and delay up to 2 nanoseconds. And then every second shot is blocked and the probe pulse hit the samples in the pump and non-pump state. So as an example, transient absorption signals can be distinguished as here, ground state bleach, excited state absorption, and also stimulated emissions. So the ground state bleach is indicated by negative delta OD, or the delta optical density, due to the loss of the ground state absorptions, while the excited state absorption is indicated by the positive delta OD, which accounts for the transitions from the excited states of the molecules to a higher lying excited states. And the stimulated emission is also indicated by the delta OD signals, which should appear at the emission wavelength of the molecules. And then to probe the slower dynamic process in the dye-sensitized photocathodes, for example, interfacial recombinations. So we use electrochemical impedance spectroscopy, and this spectroscopic technique used AC voltage modulations across the cells and scan over a certain range of frequency. And then the current response was then used to calculate the impedance of every interface in the cells, and the impedance response is presented in the kind of Nyquist plot, that is imaginary impedance versus real impedance, and then we can extract electrochemical parameters to evaluate the charge transfer process there. So the first result is to discuss the effect of nickel hydroxide intermediates to the performance of nickel oxide photocathodes. So let's start to ask, does all nickel oxide work for photocathodes? So we might all know that various nickel oxide structures has been prepared for various applications, such as for energy storage and also sensors. But we also should know that it is known typically nickel oxide is also formed by thermally annealing of nickel hydroxide. So here we should note again that nickel hydroxide has different polymorph. Yeah, mainly there is alpha, beta, and gamma, but mainly alpha and beta phase, which is discussed here. Where alpha nickel hydroxide contains water molecules within the interslab spacing, while beta nickel hydroxide contains only water molecules on its surface. So in this case, we prepared mesoporous nickel oxide nanostars. Here we got nanostars using nickel chloride precursors as a benchmark structure, but we also prepared a dense nickel oxide nanoparticles from nickel acetate and also porous nickel oxide nanoflakes from nickel sulfate. So to have a quick test here, so we check the cathodic photocurrent generations by using different nickel oxide nanostructures that we have synthesized before, and then we record the photocurrent generations using benchmark organic push-pull dye sensitized nickel oxide photocathodes in either dye-sensitized solar cell or dye-sensitized photoelectrochemical setup. So as we can see here, there is a significant difference between the performance of nickel oxide nanostars to the other structure. And then we might raise the questions why it is so different. So to unravel the origin of this discrepancy, so we have characterized the specific surface area, the porosity, microstructural, and also electronic properties. So for example, here we first monitor the formations of nanostars during the synthesis using Raman spectroscopy and TEM EDX. And from the Raman spectra and also EDX both indicates that the formations of beta nickel hydroxide reforming the nickel oxide nanostars. And this is corroborated by thermographimetric analysis in which nano stars, here the black one, underwent significant mass loss at a lower temperature due to the evaporations of the surface water molecules, which is typical for beta phase. While the other structures, for example, nickel oxide nanoparticles and also nanoflakes, they deform at the higher temperatures, which means the water molecules is trapped within the interslab spacing of the polymer of alpha. And then the structure and electronic properties of nickel oxide is now examined using X-ray diffractions. And as an example here, I show the diffraction pattern of nickel hydroxide preforming the nanostars and the diffraction patterns of nanostars itself. So it is confirmed from the phase matching and refinement that nickel oxide is cubic bunsenite. Yeah? And to further explore the electronic properties, we have examined the Fourier map derived from the diffraction pattern that is extracted from the structure factor or F here, which is a factor with magnitude and phase from all scattering point of the all observed diffraction planes within the unit cells. And then while the phase later can be estimated or calculated from the Rietveld refinement. So then the charge density can then be obtained and also visualized from the reverse Fourier transform and presented in 2D maps or 3D maps. But here I only use 2D maps to show the distributions of charge density within the unit cells. So here we compare all three nanostructures, and it is obvious there that the electronic nature is different. And nanoflakes, for example, here, which is predominantly from alpha nickel hydroxide, has charge distributions within the unit cell, which might due to ionic impurities in the intersub spacing. For nanostars, which is formed from beta nickel hydroxide, has positive charge distributions at both nickel and also oxygen atom. Meanwhile, the nanoparticles, which is obtained from the mixed alpha and also beta nickel hydroxide, has mixed character of charge distributions both in nanostars and also nanoflakes. And then We further examine the dye loading of different dye using different anchoring group, for example, pyridine, carboxylic acid, phosphonic acid, and try to correlate with the surface area of nickel oxide obtained from the BET measurement. So the dye loading here was estimated from the dye desorption test, from a square nickel oxide electrode, and summarized in the table in the slide here. And as we can see here together, that the nickel oxide nanoflakes, which has the largest surface area, shows the lowest dye loading. While the nano stars, which has a moderate surface area, shows very high dye loading, which is like sometimes 5 to 10 times higher than other nanostructures. So these results suggest that the surface area doesn't determine the dye loading on nickel oxide. So here we find that the electronic properties of nickel oxide nanostars is favorable for dye sensitizations, because from the electronic nature of the nickel oxide nanostars, the positive charge density at nickel atoms could facilitate the covalent bonding with the carboxylic acid or phosphonic acid anchoring group from the dyes. And this is further confirmed from the performance of nickel oxide photocathode itself involving the electrochemical impedance spectroscopy, and also from current voltage measurement. So the impedance analysis indicates that nickel oxide nanostars has the highest recombination resistance compared compared to the other structures, as well as the longest living valence band hole from the T here, which is extracted from the electrochemical parameters after fitting. So the effective diffusion length also suggests that we are able to prepare thicker film for using nickel oxide nanostars by factors almost 2, so that the current thickness, which is 1.5 micrometers, can be doubled up to 3 micrometers thick. But from the solar cells properties, nickel oxide nanostars also shows the highest photoelectrochemical conversion efficiency, which is I would say it's on par on the best reported efficiency of nickel oxide-based solar cells prepared under similar system. So here we conclude that nickel oxide nanostars, which is preformed from beta nickel hydroxide, is promising for further development of photocathode materials. So having discussed the electrode materials, now we shift our discussions to the dynamics of the charge separations at the ruthenium sensitizer and nickel oxide interface. So as mentioned earlier, we employed ruthenium polypyridyl complex with dipyridophenazine or DPPZ ancillary ligands. Here, the BP, the bipyridine anchoring ligands, here is extended also with conjugated linker, that is phenylene and also phenylene triazoles. As we see in the absorption properties, putting conjugated linkers shift the visible absorptions to the red. Here, indicating that the electron delocalizations on the extended BP ligand. So in addition, the emission properties, the emission maximum, is blue shifted, in which the quantum yield of ruthenium L0 means without linkers, increases upon additional linkers, indicating that the contributions from the PP ligand to the emissive triplet MLCT state other than the DPPZ ligand or the pyridophenazine ligand. So to quickly check that this complex work for nickel oxide photocathodes, we perform time-resolved emission spectroscopy for both dyes in solutions on inert surface of zirconia and also on nickel oxide. So as can be seen here, emission lifetime of the dyes in solution is rapidly quenched when the dyes are adsorbed on the nickel oxide surface. Meanwhile, the emission lifetime is slightly shorter on inert zirconia surface, where charge injection should not take place. So therefore, in this measurement result, the rapid quenching of the emission lifetime indicates that the whole injection occurs on the interface of the ruthenium sensitized nickel oxide surface. So from the to understand the localizations of excess charge density upon optical excitation at the MLCD band, resonance Raman measurement at different excitation wavelength is carried out. So the Raman band of the DPPZ and also PP ligand is indicated by the blue and also the green, yeah, respectively. So the blue is the DPPZ ligand, and also the green is the piperidine ligand. So here is the intensity ratio of Raman signals assigned to the DPPZ to the PP ligands at different excitation wavelength, which reveals that the localizations of the Frank-Condon region within the complexes. So for ruthenium L0, yeah, without the linkers, the Raman intensity of DPPZ increases at a longer wavelength, while it decreases for ruthenium L1 and ruthenium L2, yeah, here and here. And this result indicates that additional linkers for ruthenium L1 and ruthenium L2 introduced in ruthenium lowers the PP associated lumos energy. So that's why the charge density shifts toward the anchoring ligands here. So the charge density is shifted from the DPPZ toward the PP ligands if we add additional linkers. So this is of course not expected for P-type dye-sensitized solar cells, as I introduced in the beginning, that the charge density at the PP ligand will screen the whole injection. So let's see what happens when we shift our charge density from the periphery of the molecules and close to the nickel oxide surface, for example, in this two extended ruthenium complex. So here is the transient absorption spectra of the ruthenium L0 and ruthenium L1 after excitation at 480 nanometers. So the assignment of transient absorption species is supported by the absorption difference spectra obtained from spectroelectrochemistry after applying potential at the PP and DPPZ ligand reduction. So it is indicated by the gray and also the blue shadow. So both complex in principle, yeah, show the ground state bridge, which is negative here, and also excited state absorption signals, which remains around like 80% within our experiment time window, which is 2 nanoseconds. A slight difference is observed for ruthenium L1 with vanillin linkers, where there is a shoulder here at 530 nanometers associated with PP ligand, yeah, which decays around 10 picoseconds, and then followed by the building up of 600 nanometer signals. So here we assign that this phenomena corresponds to interligand electron transfer transition from the PP to DPPZ ligands. So to quantitatively analyze the data, we perform global fitting to the transient absorption spectra, yielding the decay associated spectra like this. So for example, for ruthenium L0, we have sub-picosecond decay component, which is 0.2 picosecond, which reflects the contributions of intersystem crossing and also intramolecular vibrational distributions. And then we have the second component, which is at 46.3 picosecond, which shows a build-up of signal at 600. Oh, my cursor doesn't show. Yeah, at 600 nanometers, which can be assigned to intraligand charge transfer, transition from phenanthrolene to phenazine part of the DPPZ, and the final process, which is longer than 2 nanoseconds, is indicating the return of the excited states to the ground state of the complex. So the excited decays of the excited state decay of all complex then can be illustrated in the energy diagram as follows. So the ground state absorption induce the first excitation at the singlet MLCT stage, and then there is intersystem crossing, there is ILCT, and then decays back to the ground state level. So now we look at the transient absorption spectra of the complex immobilized on nickel oxide. So the transient absorption spectra here looks different from those measured in solutions here. So this indicates at least the first interactions at the interface of the dye-sensitized nickel oxide. So what we do next is to globally fit again the transient absorption data on nickel oxide, and the decay associated spectra is also presented as follows. So we have the first decay component, which is characterized time constant of few picosecond which shows negative delta OD signals, even though it is less prominent, but this reflects the build-up of oxidized nickel and reduced complex, and therefore it is assigned to the whole injection process. While the decay spectra with time constant of several hundreds picosecond, which is and beyond 2 nanoseconds, which is marked with the decay of positive delta OD signals here, is assigned to the decay of PP and also piperidine and also DPPZ based charge separated states respectively. So here is some illustrations. So upon photoexcitations, there is charge separations that creates radical anions in DPPZ ligands or the extended PP ligands. So the whole injection is then screened by the charge accumulations in the extended PP ligands. So in this case, again, it shows destabilizations of the charge separated states. Why? Because we want to have more charge density away from the nickel oxide surface. And this is only possible without linkers, unfortunately. So this is actually not by design, but accidentally, by accidents, we found this interesting phenomena and try to correlate with the device performance. And then this is the time scale of charge separated states decay. You can just easily see the number there. And this is the solar cells performance. Because of the screening of whole injections by the charge accumulations on the PP ligands, here we can see that the molecular electron transfer density at the dye-sensitized interface or dye-sensitized nickel oxide interface is higher for ruthenium L0 without the linkers. And the additional of the linkers will harms the whole injection and also lower the performance of the dye-sensitized photocathodes. Okay. So last sections of these presentations, we now turn our attentions to the effect of applied bias to the charge separated state stability in a quite similar system to ruthenium DPPZ sensitized nickel oxide. So here we have ruthenium platinum catalyst sensitized to nickel oxide. As illustrated in this.
5 minutes remain. 5 minutes remain. 5 minutes remain.
Yeah, sure, Bu Lucy. Will do. So, as illustrated in this slide, we applied DC voltage bias, both positive and also negative into the dye-sensitized nickel oxide with and without passivations with aluminum oxide. So now we want to try to evaluate the transient absorption spectroscopy of this system. So the transient absorption data of ruthenium platinum sensitized nickel oxide is shown here. So based on spectroelectrochemical data, we distinguish the TP base and also TPPHC base charge separated states according to the signals at 380 nanometers and also 650 nanometers. And then we want to get quantitative value of the charge separated state stability. So we make another delta OD, difference absorption, which is calculated as follows. So the delta OD is actually the subtraction between the signals at short delay times, which corresponds to the initially formed charge separated states, and the signals at the longest delay time, which indicates the remaining charge separated states within our experimental window. So here, smaller delta OD means more stable charge separated states, while higher delta OD indicates destabilizations of charge separated states. So the result shows here that at positive bias, we can see that the delta OD signals increases, indicating the destabilizations of both charge separated states. And this is plausible, because if we apply positive bias, then we will increase the non-geminate holes on the nickel oxide. We put more holes on the nickel oxide, and then recombinations becomes more probable with radical anions. But at negative bias, what happens? at negative bias, we expect the charge spreaded state will be stabilized, yeah, since we extract all non-geminate holes from the nickel oxide surface. But if we can see here, as we can see here, the result shows that it's true. Okay, for the TPPHZ, yeah, it becomes lower, yeah, it becomes stabilized. But why for the PP it becomes destabilized? It's increasing at more negative bias. So to get the answer, we check the kinetic traces at 380 nanometers and 650 nanometers associated with the BP and the TPPHZ ligands, respectively, under different applied bias. So as shown here, under negative bias, yeah, both BP and TPPHZ signals decays, but after 100 picoseconds, we can see here, yeah, the TPPHZ signals builds up. However, under zero and positive bias, both signals only decay up to the longest experimental window. And this, we suggest that the BP anion is pushed toward TPPHZ ligands, which is possibly due to the Coulombic repulsions by the external electric field. So, yeah, to close the presentations, because the time is up, yeah, I will summarize what I talked about in 3 different sections before. That I have first shown that nickel oxide prepared from the beta nickel hydroxide is preferable for photocatalysis in dye-sensitized photoelectrochemical cells because the electronic nature allows for covalent bonding with different anchoring groups of the sensitizer. And then from the second part of my presentations, I have shown that the extending of the conjugated electronic system lowers the accepting orbitals of the PP ligand. And this leads to the shorter charge spread state lifetime in the ruthenium DPPZ sensitized nickel oxide. And finally, if we apply negative bias at dye-sensitized nickel oxide, this enables stabilizations of charge separated states by reducing the non-geminate recombinations, and yeah, quite significantly prolongs the charge separated states lifetime. Yeah, that's all from my presentation from my side. Yeah, but I would like also to thank my previous supervisor, Professor Ditzek from University of Vienna, whom I have been working with, and also other collaboration partners from OSIM, Jena, from Ulm, from Renewable, and from New Brunswick. And also I'd like to thank my colleagues from IG Ditzek at the FSU Jena, and also Leibniz IPHD in Jena, and also DAD and TAB, Thuringia Aufbaubank, for the financial support during my work in Jena that I presented today. So that's all from my side. Thanks, Bu Lucy. I'll give it back the sessions to you.
Okay, thank you very much, Dr. Duri. As I mentioned, photocatalysis is considered as a promising route to convert and store solar energy. In terms of its large-scale application, seeking semiconductor photoelectrode with high efficiency and good stability is very essential. Very comprehensive presentation, great research, and it will be good for the discussion in the last session. I hope there are many questions was prepared by some of participants related with this topic. Well, now we are going to the next presentation that will be delivered by Dr. Wibawa Hendra Saputra, as commonly addressed as Dr. Hendra. Before Dr. Hendra start the presentation, let me introduce his short profile. Dr. Wibawa Hendra Saputra is currently lecturer at the Energy and Chemical Engineering Processing System, Department of Chemical Engineering, Bandung Institute of Teknologi. His research emphasizes on the development of photocatalysts and electrocatalysts for various applications, including wastewater treatment and carbon dioxide. Carbon dioxide reduction into fuel and value-add chemicals, and development of catalytic ozonation technology for wastewater treatment as well. Dr. Hendra will deliver the presentation with the topic photocatalysis as a promising technology for environmental remediation and energy conversion. Dr. Hendra, are you ready? Time is yours.
Okay, thank you, Bu Lucy, for the short introductions. Can you hear my voice clearly?
Yes, very clear.
Okay, so let me share the slide first. Okay, is the slide visible?
Yes, it's visible and clear.
Okay, thank you very much, Bu Lucy. So it is an honor for me to be invited as a world-class professor program lecture series 2022 held by the Institut Teknologi Kalimantan. Ya, salam kenal untuk Pak Ruri, Pak Jaka dan Pak Hairus. Ya, so good morning, everyone. So for today, I would like to give the talk regarding the photocatalytic as a promising technology for energy conversions and environmental remediations. So this is my outlines of the presentations for today. So including the short introductions, research focus, research background, principle and mechanism of photocatalytic technology, my current research findings, future prospect of photocatalytic technology, and will be closed by the concluding remarks. Okay, so let me briefly introduce myself first. So I am Ibu Hendra Saputra, so commonly called Hendra. So I did my bachelor in chemistry ITB under supervisions of Muhammad Abdul Qadir Matapawiro with the research topic of the computational chemistry, and I continued doing the double degree programs in chemistry ITB and chemical engineering University of Twente. So the research is under supervisions of Professor Guedemul and Dr. Hamdi Saad with the research topic of photocatalytic wastewater treatment, especially using the textile waste or using a dye model compounds. And continuing doing the doctoral degree at Chemical Engineering, University of New South Wales under supervisions of Professor Ross Amal and Dr. Jason Scott with the research topic of photocatalytic organic oxidations. And I did also the 4 months postdoc at the same place, Chemical Engineering, University of New South Wales with same supervisors and other topics. This is my research focus. So coming from the problems actually occurred in the world, consisting of the air pollutions, energy crisis, and also the wastewater pollutions. To mitigate these issues, so I tried to develop the novel catalysts, including the electrocatalysis or photocatalytic technology. But for today's talk, I will focus on the photocatalytic technologies, which I divided into 5 classifications in these cases. So the first one is for wastewater treatment. So I have actually developed these technologies for mitigating waste problem, including the textile waste, pharmaceutical waste, and also the palm oil mill effluent waste generating from the palm oil industries. The second one is for water splitting, where the photocatalytic technologies can convert water into hydrogens and oxygens. The third one is for CO2 reductions, where the CO2 can be converted into value-added chemicals, such as formic acid, methanol, ethanol, ethylene, and so on. The fourth one is for methane oxidations. So the methanes hopefully can be converted into the methanol as one of the main commodities, especially in Indonesia. And the last one is, this is actually the new applications for the photocatalytic technologies, which just published in Nature Catalysis in 2020, where the fatty acid can be converted into the biohydrocarbon, where this biohydrocarbon can be used as a backup for the gasoline or diesel, or maybe the after as fuels for the transportations. Okay, so coming from the backgrounds where we have the around 1.2 million tons with 10,000 different synthetic dyes and pigments, and also coming from the several industries, including the textile waste, pharmaceutical waste, and also the palm oil waste, where Indonesia is actually one of the largest producer for palm oil. So where it actually will consequently produce also very large amount of the waste. So in these cases, around 10 until 15% are lost in industrial effluents, which causes the environmental pollutions, especially for the water ecosystems. On the other hand, we have also the emissions coming from the greenhouse gas. One of them is actually CO2. So based on this graphic, we can actually see that the CO2 mainly coming from the industrial activities and followed by the electricity and heat and also the transport. And based on the WHO data, where more than 95,000 people in Indonesia die every year due to CO2 pollution. Therefore, based on these problems, so we have to mitigate these issues by providing the solutions. So what is the solutions? What is the technologies that can be developed to solve these problems? So there are actually several technologies which has been actually developed, such as membrane bioreactors, membrane nanofiltrations, reverse osmosis and membrane, thermochemicals, electrochemicals. However, this kind of technologies, especially for the membranes, have several disadvantages. Yeah, for instance, the membranes can be easily destroyed if they use kind of the specific solvents. And also for the thermochemicals, it's actually operated under very high temperature and also very high pressure. While for the electrochemicals, it's actually using the electricity to as a driving force here to activate the catalyst. So in this today's topic, I will focus on the photocatalytic technologies. Yeah. So because photocatalytic technologies can actually deliver several advantages. For instance, the photocatalytic is actually cheap price because the raw material is very abundant, easy to get, and also very cheap. And photocatalytic also environmentally friendly because it can convert the organic contaminants to CO2 and water as a final products. And it's actually energy saving because it's working under ambient conditions. So at room temperature and also at atmospheric pressure. So initiated with the UV and visible light. And it's also sustainable technologies because the catalyst can be actually reused for several cycles until it's actually saturated. So this is actually the examples where the photocatalytic actually already implemented in the large scale applications. For instance, in Germany, they actually use it as for the wastewater treatment system. In Rome and also in Brussels, they use it coated in the building and also in the tunnel for air purifications. So the basic of using the photocatalytic technologies is actually our goals or the main goals of photocatalytic technology is how we can actually utilize the solar, because the solar in here, as denoted in the figure on the left hand side, is actually will actually generate very high amount of the energy, around 173,000 terawatts, where based on the spectrum of the solar irradiations, so they use UV for around 2% and visible and infrared is around 45 until 50%. So that's why in here we try to mimic for the photocatalytic technologies where we can actually use this kind of the spectrums, whether we use the visible or maybe the infrared to drive or activate the catalyst in order to perform the redox reactions. Let's go on. So as we know, the solar energy is the most abundant energy source on Earth, and Indonesia especially receives around 3.6 until 6 kilowatt-hour per meter square per day of solar irradiations intensity, where it's actually equivalent to around 1,100 until 100,500 kilowatt per hour per kilowatt peak. So that's why the utilizations of the solar energy is actually very, very beneficial, especially in Indonesia, especially for the photocatalytic processes. So what is photocatalysis? So photocatalysis is actually the accelerations of the reactions. So using the catalyst and also using light as a driving force. So where we use the semiconductor-based materials where they have very small bandwidth between the valence band and conduction bands. And there are several catalysts that has been developed. One of them, which is actually already commercially available, is actually TiO2. Where TiO2 have the band gap around 3 until 3.2 electron volt, which can be activated by the UV light. And the photocatalytic technologies in these cases have been developed also for several applications. So two of them is for CO2 reductions and also wastewater treatment. So this is actually the main schematic of using the photocatalytic technologies for CO2 reductions. So where we have the light source where the energy is actually higher than the band gap. it is actually can be activated, the catalyst, by exciting the electrons from the valence band and conduction bands. So in the conduction band, the electrons will be consumed by CO2 and reduce it to solar fuels, where the solar fuels, including the formic acid, formaldehyde, methanol, methane, or syngases, and in oxidation part, the water will be actually oxidized to form the oxygens, or we call it the oxygens evolution reactions. Where in the wastewater treatment, the concept is almost the same, but only the different reactants that is actually used to perform the redox reaction. So in the conduction band, commonly for the wastewater treatment, we purge the system with the oxygens, and the oxygens will react with the electron to form the radical oxygens, and the water at the conduction and at the valence band will be react with the holes to create the hydroxyl radical. And these two radicals is actually very reactive, and it will actually destroy the organic contaminants, including the textile, wastewater, pharmaceutical wastewater, pomade wastewater, and other type of the wastewaters generated from the industries. And this is several applications of the photocatalytic technologies rather than wastewater treatment and CO2 reductions can be also used for the water splitting, methane oxidations, bacteria removing, air purification, and etc. So the TiO2 photocatalysis is one of the abundant and also commercially available in recent times. And from the crystal structures of TiO2, consisting of the 3 different crystal structures, which is anatase, rutile, and brookite. And from the references, the TiO2 anatases is reported as the most active crystal phase compared with the rutile and brookite phases. But at the moment, the commercially available is actually the mixtures of the anatase and rutile, where we call it P25 degussa, where consisting of the 80% of anatase and 20% of the rutile. And it is actually reported that this mix of the crystal phase structures is actually more active compared with the anatase alone. However, the limitations of the TiO2 photocatalyst, it has actually insufficient utilizations of the visible light because it can only activated by using the UV light, high electron and hole recombination rate, because the lifetime of the electron in the conduction band is actually very short. And it tends to form also the aggregations of the nanoparticles as well as the low adsorptions of the organic pollutants. Therefore, to improve the photocatalytic activities for the wastewater treatment or CO2 reductions, there are actually several steps that can be actually used, such as doping, surface modifications, heterojunctions constructions, or by doing also the vacancy introductions of defect generations. So one of the strategies to increase the photocatalytic activity by creating the defects. So for instance, in here, I have the TiO2, where the TiO2 for the stable conditions, it has the oxidation number of Ti is 4+. So in here, try to generate the Ti3+ defects associated with the generations of the oxygen vacancies. By creating these defects, it can actually lower the band gap of the photocatalyst. So lowering the band gap of the photocatalyst will be indicated the energies needed to activate the catalyst will be much more lower or can be activated by using the visible light. Yeah, this is actually several constraints that will be overcome by several research that has been actually reported by our research groups. So the constraints in here is actually recombinations of electron and holes, as I mentioned before, very low UV and visible light absorptions, and also the catalyst stability is actually still very low. So in here we have three strategies like metal doping, heterojunctions for the catalyst, and also generations of the cation and anion defects. On the right-hand side is actually just the schematic illustrations how these strategies actually can be worked. And the idea of doing these strategies is actually to increase the lifetime of the electrons in the conduction band, as well as to reduce the band gap in order to can be activated by using the visible light with the lower energy compared with the UV light. Okay, so I move on to the first applications where our research group has been actually reported. But for these environmental remediations, I focus on the textile waste, pharmaceutical waste, and also for the palm oil mill effluent waste. Yeah, starting from these concepts, where I use the defect generation strategies where I create the titanium 3+ in the titanium dioxide anatase. So the methods to create these defects is just simply mixing the TiO2 anatase with the Ti2O3. So the TiO3 in here is actually not active photocatalyst. Yeah. So we try to mix it with the TiO2 anatase to create the titanium 3-pos self-doped into the TiO2. So the ratio of these two mixtures is actually 1:1, and I calcine at 300 until 900 degrees Celsius with the ramping rate of 5 degrees per minute for 3 hours. And it is actually very interesting where we can actually see that is actually the changing of the colors, yeah, by increasing the temperatures of the calcinations from 300 until 900. So the colors is actually gradually changed from gray, light gray, and interestingly at 600 degrees it's actually form yellowish color. And at higher temperature, at 700 until 900, it's actually formed the white color. So by looking at this visual appearance of the catalyst, so we try to characterize this catalyst by using several instruments. So for the X-ray diffractions, it can be seen that the catalyst that is actually calcined at 300, it is actually still formed in the anatase phase, where at 600 degrees, the rutile phase, there is actually transformations of the crystal phase structures from the anatase to rutile, where we can see that it's actually gradually increased, yeah, from 600 and 900. There is actually the mixtures between the crystal phase of the anatase and rutile. And it's actually confirmed by the Raman spectroscopy as well. Yeah, at M300 there is no rutile phase appeared, but for the 600 and 900 calcination temperature, the rutile phase is actually generated. Yeah. And also, we try to confirm the presence of the defects on the structures, which is actually the titanium 3+, and it is actually confirmed by using the XPS, X-ray photoelectron spectroscopy, where the titanium 3+ is actually appeared in the surface of the catalyst. And we try to also investigate the appearance of the titanium 3+ on the bulk structures of the TiO2 by using the electron paramagnetic resonance. And it can be seen that at 600 degrees C and also the 300 degrees C, the titanium 3+ is actually appeared, yeah, which actually indicated that the generations of titanium 3+ is actually successfully done, yeah, in this type of the catalyst, which can actually later on very beneficial to improve the absorption's efficiency and also can be activated under visible light absorptions. And based on the UV phase absorption spectra, we can also see that the M600, which is actually the yellowish titanium dioxide colors, is actually absorbed under visible light range, yeah, where for the 301 is not actually active under visible light, yeah. And also from the BET measurements, the surface area is actually gradually decreased by increasing the temperature or calcination temperature, which is actually agreements with the theoretical fundamental aspects. And based on the scanning electron microscopy, it can be also seen that there is actually the defected titanium dioxide rutile is actually generated, yeah, where at 600 degrees C, there is actually the mixtures between the rutile and also anatase, where there is actually also the titanium 3+ defect generated in this TiO2 systems. And move on for the photocatalytic activity. I used very simple apparatus in here, just using the beaker glass, 100 ml beaker glass, and I used the UV light. So this is the UV light with the powers of just 18 watts. So we have around 5 UV light in these cases, and I purge with the oxygens during the photocatalytic activity measurements. And this is actually the operating conditions that I use with using the methyl orange as a model compound and also methylene blue. And it can be seen that in here, it is actually proof that the methyl orange is actually degraded, yeah, as a functions of time. It's actually also in line with the concentrations that is actually detected from the UV-vis absorption spectroscopy. And based on the photocatalytic activity, it can be seen that the TiO2 anatase mixed with the Ti2O3 is actually more active compared with the TiO2 rutile and also without the catalyst, or we call it the photolysis. Yeah, for the photolysis processes, there is no degradations of the methyl orange, and it can actually confirm also in the right-hand side table where the M600, which is actually the yellowish color of the TiO2, is the most active catalyst compared with other calcination temperature and also the control temperatures like the TiO2 P25, which is already commercially available at the moment. and TiO2 anatase, as well as the TiO2O3. And follow by the doping with the several metals, because the the mixtures of the composites of the TiO2 under 600 degrees Celsius calcination temperatures give the most active catalyst for the metal orange degradations, and try to dope with the several metals to improve the efficiency of degrade the metal orange compounds. So in these cases, I dope with the platinum, gold, and copper. And it's actually some of them is actually not. There is no actual difference for the XRD patterns, because the size of the metals is actually very small, so it can't be detected by using the XRD, but it can be actually detected by using the SEM, where there's actually a small dots in here, small dots indicating the presence of the platinum on the TiO2 surfaces, which means that the metallic platinum is successfully synthesized on the TiO2 composites nanoparticles. And for the photocatalytic activity, we can see that by using the platinum dope on M600, or the composite which calcine under 600 degrees C, it actually increased the activity for the metal orange degradations up to around 3 times, compared with the M600. While for the gold and copper, it's actually give the lower activity due to the less amount of the surface hydroxyl groups, and also the particle size of the metal is actually too big, which actually can inhibit the catalytic efficiency of the mixtures of the TiO2 itself. And I did also the stability of the catalyst. Yes, for the M600 is actually gradually decreased, but for the platinum dope on M600, for the second cycles is actually almost the same. There is no significantly decrease, but for the third cycles, it decreased up to 1.4 times compared with the first and also the second cycles, indicating that by using the metals dope on the M600, it will give or enhance not only the photocatalytic activity, but also the stability of the catalyst. And move on for the next one, which is actually the hydrogenated titania. So previously we mixed the TiO2 and TiO2O3 to create the titanium 3+. So for the second methods, I use the TiO2, the commercial ones, just hydrogenate at various temperature. So I purge the hydrogens and also heat it up until 400 until 700 degrees C for 5 hours with a flow rates of 20 mL per minute. So we can see that there is actually different colors generated, starting from the yellow, white, yellow, and also the gray colors, And for the P indicating for the P25, H indicating for the Hombicat or anatase, and R is actually the rutile. So we can see in here that the HP 500 in these cases give the very promising photocatalytic efficiency. So comparing with other catalysts, it's actually give very high photocatalytic activity. And I did also the same thing, the stability of the catalyst, for the hydrogenated one. We can see that for the hydrogenated with the platinum is actually still significantly decreased, from the first cycle until third cycles, as well as for the hydrogenated without the presence of the platinum. Okay, so move on. So the two previous work is actually conducted when I did my master's in University of Twente, and I tried to develop my own laboratory in chemical engineering laboratory. And at the moment, we have actually 2 configurations of the reactor, which is actually the Immerse Illumination Reactor as illustrated in this figure, where the lamp is actually in the centers of the photoreactors, in order to make the illuminations more homogeneously dispersed in the system, where we also circulate the cooling water using a chiller in here to make sure that the reactions processes is actually conducted under the ambient conditions, because we actually use the 300 watts of the xenon lamp in this system, so it actually can generate the heats during the processes. So that's why in here we try to balance it by circulating the chiller water to the system to make the temperature operating conditions still under ambient conditions. And the second configuration type of the reactor, we call it top illuminations reactors, where the light is actually coming from the top, to the bottom of the reactor. So this is actually the reactors. For this system, it is actually already configured by using the cooling fan. So we don't need to circulate the cooling water into the system, because this system is already use the cooling fan to make sure that the temperature condition is still under ambient conditions. Okay, so the next one is actually for the POME degradations, palm oil mill effluent degradation. So previous one we focused on the textile water. So I developed also the catalyst other than titanium dioxide. I tried to develop the bismuth vanadium photocatalyst. So this is actually the method where we actually mix it between the bismuth nitrate, citric acid, and also the nitric acid, and mix it with the ammonium vanadate and also the citric acid as well as the ammonia. Mix it and heat it at 75 degrees C and calcine at different temperature. And we can see that there is actually a yellowish color generated in here. And we try to characterize the samples. So it is actually very interesting, because in here we can see that there is actually two different crystal structures phases for the bismuth vanadate, including the tetragonal phase and also the monoclinic phase, where when it actually calcine at 300 and 375 degrees C, so it is actually still mostly in the tetragonal phases, but by increasing the temperature, we can see that there is actually the transformations occurred where the monoclinic phase is also generated. And it is also confirmed by using the Raman spectroscopy, where at 375 degrees C there is no tetragonal phases, and it's actually totally transformed into the monoclinic phases. And this is actually the same images for the photocatalyst of the bismuth vanadate at different temperature, 300 until 600 degrees C. And we did also different characterizations. So UV-vis diffuse reflectance spectroscopy, so where we have also, or we can calculate the band gap of the photocatalyst by using these characterizations, and it can be seen that the band gap of this photocatalyst is actually lower compared with the titanium dioxide. So it's around 2.4 until 2.5 electron volt, which indicated that this type of the photocatalyst can be actually activated using lower energy or visible light energy. And we try to do also the electron paramagnetic resonance in order to find out whether there's actually a defects structures in this system. And it is actually proof that the defects generated as well, which is actually the vanadium 4+ associated with the oxygen vacancy. And we can see that there is actually a trends in here where the bismuth vanadate calcine at 450 degrees C. It generates the most defects compared with other calcination temperature. And if we have a look through the photocatalytic activity performance, we can see that it is actually mimic the defect generations as illustrated from the electron paramagnetic resonance characterizations, where the BV 450 degrees C give the best performance compared with others type of the catalyst. So indicating that there is actually a correlations between the defects once again, and also the photocatalytic performance of this catalyst. And on the below figures sections in here, so we also calculate the rate constants of the based on the pseudo first order kinetics, and it actually confirmed this trends with the defect generations as illustrated from the EPR measurement. Okay, so we move on to the second applications, which is actually energy conversions. So we focus on the photocatalytic CO2 reductions into value-added chemicals, especially for the methanol productions. So we develop the copper titanium dioxide zeolite, in this cases for the CO2 reductions to methanol. So this works is actually in collaborations with the Engineering Physics ITB and also the National University of Singapore and US. And this work is actually done by the bachelor students, Adi and also Dozi, And we try to synthesize the copper-based catalyst, where we want to find out the roles of the metallic copper and also the oxide copper for the CO2 reductions. So we synthesize first the titanium dioxide coupled with the zeolite. So the type of the zeolite that we use is actually ZSM5. Yeah. And we did also the synthesis of the catalyst by impregnating the copper into the titanium dioxide and zeolite, consisting of the CuO on TiO2, metallic copper on TiO2, as well as the oxide copper and metallic copper in the TiO2 zeolite catalyst. So we did several characterizations in here. Yeah, so the XRD patterns and also the PET. So we can see that by using a zeolite as support in these cases, we can see that the specific surface area is significantly improved compared with only using the TiO2. So it's almost around 40 times, yeah, compared with the copper that is actually doped on TiO2. And from the same EDX measurements, it can be also confirmed that the copper is actually homogeneously dispersed into the zeolite and also the TiO2 itself. And from the UV-Vis DRS, it can be seen that the band gap also can be calculated, where the CTZ1 and 2 is actually in interval of the band gap from 3.3 until 3.4, because it consisting of the zeolite structures, where the zeolite is actually acted not as a semiconductor. So the band gap of the zeolite is actually very, very high, which is actually can be attributed to this improvement of the band gap compared with the TiO2, where the TiO2 is around 3.25 until 3.28 electron volt. And we did also the CO2 TPD. So in order to find out the basicity sites, yeah, of the catalyst, yeah. So it can be seen in here that there are actually two peaks generated, yeah. So at the low temperature and at the higher temperature, where it's actually indicated as a weak basicity site and also the strong basicity site respectively, yeah, for the catalyst. So it can be seen that there is actually an improvement where we calculating the basicity sites, yeah, where the CTZ2 have 5 times increment compared with the TiO2. So the higher the basicity site, later on can be actually beneficial for the CO2 for reducing the CO2 into the specific products. And
Excuse me, Dr. Hendra.
Yeah.
Your time is up.
Okay. So
I think 5 minutes you can.
Okay. Yeah, I will do it. Okay, so in these cases, we can see that the methanol is actually generated, yeah, in here, yeah, where we have the CTZ1, where CTZ1 is actually the oxide one. So based on these cases, the copper in the oxide form is actually very beneficial for the CO2 reductions. And for the cycling also is actually very stable, yeah, so around 0.6 millimole per gram catalyst in these cases. So so we want to find out, yeah, and we still under this work is actually still under progress, because we want to investigate or doing the characterization, especially for the X-ray photoelectron spectroscopy, to find out the amounts of the copper in the form of the metallic and oxide, yeah, and also we try to collaborate with the engineering physics to do a simulations, density functional theory calculations. Okay, so this is the ongoing research that we actually done. So in total, at the moment in the lab, we have 1 student from the doctoral degree, 6 students from the master degree, and also 10 students from the bachelor degree with this kind of topics. Yeah. I just try to give you in 5 minutes for the future outlook of the photocatalytic technology. So the first one, of course, the development of visible light active photocatalysts, because our main goals is actually to utilize the solar energy, which consists mostly is visible and also near infrared regions. Yeah, so that's why in here we try to develop the catalyst that can be activated under visible light. And yeah, if we have looked through the larger scale of the applications, so some of the company already tried to improve, yeah, the TRL or technology readiness level of the photocatalytic processes. For instance, CZG Plasmonics developed photocatalytic chemical system, and they actually stated that this is actually the world's highest performance for the CO2 reductions into the value-added chemicals. And in the Panasonic as well, the photocatalytic water purification technologies is actually developed to create the drinkable water with sunlight and photocatalyst. So this is actually the illustrations that should be actually implemented in the near futures where they use the solar power as photoactivating catalyst and also the photocatalytic systems actually used to remove the bacteria removal and also to purify the water, and it can be used for the drinkable water later on. And they can also try to develop the air conditioning AC with photocatalytic technologies for air purifications. In these cases, they develop or try to integrate the technologies between the photocatalyst using also the plasma ionizer and so on. So the photocatalyst is actually combined to also remove the bacterial removals and also to get the more purified air. And the last one is for photocatalytic CO2 reductions to methanol. So hopefully in the near futures, this can be also implemented, especially in Indonesia, where we can actually utilize the CO2 generated from the flue gas in power plant. And later on, we create several utility systems, including the CO2 capture unit, photocatalytic reactor, separation plant, and also later on, we can create the methanol with the high purity, and also use for the one of the biggest chemical commodity in Indonesia. And the last one, this one, the breaking news, as we know that the BBM is actually increased the price, from, this is actually the current price of the type of the gasoline that we have, and also diesel, and it is just reported on 2020 that the photocatalytic technologies can be also convert the fatty acid into the biohydrocarbon, where this biohydrocarbon is actually can be used as our backup, to solve this kind of the problems, because at the moment, we have actually still a problem with this kind of the technologies. Okay, so this is the future outlook of photocatalytic technologies, including the energy conversion and environmental remediations. So with these technologies, these two applications can be also implemented. We can actually consider several aspects as denoted in these illustrations of the pictures. And it can be concluded from this talk that the photocatalysis is a promising and green and sustainable technologies for several applications, including the wastewater treatment, air purification, CO2 reduction, and also energy conversions. And the development of visible light active photocatalysts will be the main challenge, so that the photocatalysts can be activated under visible or even infrared to conduct the redox reactions for certain applications. And later, the last one is photocatalysis can be implemented in large-scale applications, hopefully, in the near future. So I would like to say thank you to all of the college that has actually support this work, and also once again thank you for Bu Lucy for inviting me in this webinar series. I'll give back the time to Bu Lucy. Thank you.
Thank you, Dr. Hendra. Very nice presentation. As I mentioned, photocatalyst, catalyst which is active under certain wavelength of light, and it offers solutions to the needs for both of sustainable energy and environments. It takes a full advantage of the light as the free energy to improve the environmental quality, for example, by removing organic pollutants, reducing carbon dioxide, and also provide the renewable energy. It is very nice research and well presented. And now we are going to the next presentation. At this moment, I would like to remain against to all the participants. We will have discussion session, questions and answer after all the presentation finish. For the participants who wants to ask the questions, can write it directly and in chat column and raise hand by opening your microphones. The next presentation still relates with the topics of photocatalysis that will be delivered by Dr. Hairus Abdullah. At the first, let me introduce Dr. Hairus Abdullah profile. Dr. Hairus now is a senior lecturer in Universitas Prima Indonesia, and now he is doing postdoctoral fellow in Department of Material Science and Engineering, National Taiwan University of Science and Technology, NTUST in Taiwan. And Dr. Hairus today will present the materials with the topics nanomaterials for environmental remediation and hydrogen evolution reaction, as well as the application for the hydrogenation reaction. Dr. Hairus, are you ready? Dr. Hairus?
Okay, yes, I'm ready.
All right. Now time is yours.
Yes. Can you hear my voice clearly? Hello, Dr. Rusi. Can you hear my voice clearly?
Yeah, it's quite clear, but maybe it's how to say, far from your device, I think.
Far from my device. Okay, let me try to.
Okay, now it's clear. Now it's clear.
Okay, thank you. Okay, thank you very much for the time from Dr. Rusi and for the invitation for this talk this morning. And first of all, I want to introduce myself. My name is Hairus Abdullah. And special thanks also for Professor Jaka, and then Dr. Ruri, Dr. Hendra for a nice presentation today. And today also I want to share one of my research work related with hydrogen evolution reaction and the application for hydrogenation reaction. So for today, the outline is I will a little bit talk about the introduction. So most of them already discussed by Dr. Hendra, so very comprehensive, and it was also very impressive. Then after the introduction, I will give you one of my work related with the DNOS. So this is DNOS as a storage solution. So it's also a very promising hydrogen evolution photocatalytic. And then the second one, I also want to share you with PN heterojunction. With actually the basic material is DNS, and we job with the AG and IN, and we can decrease the band gap. And after that, we composite with the P-type AG2S, and this is very promising to reduce the hexavalent chromium. And you know that toxic hexavalent chromium is very toxic. Then we can reduce become chromium 3+. Then the toxicity become less. Then finally, I will talk about the conclusion. Okay, for the introduction, just a very brief introduction. So as we know that our life have been using the fossil fuel very heavily, right? And then this carbon-based material actually release very high concentration of carbon into the air, and you know the carbon cycle in the air become imbalanced because of the high concentration of carbon. And you will see that from the 1,000 years ago until now, the carbon concentration in the air, I mean the CO2, right? So achieve about 400 ppm, like 400 ppm, and it's quite high. And that's why we feel that there's a global warming, as we know that there's a greenhouse effect from the carbon-based gases in our atmosphere, right? And therefore, there's one solution, one of the solutions, right? So as we know that it's also discussed by Dr. Hendra by using the semiconductor material. So as the semiconductor materials illuminated with the light, and then we can have the photoelectron and holes, right? So the photoelectron and holes can diffuse to the surface of the catalyst and do the redox reaction. And in this case, I will try to use the part of the reaction which is reduction reaction, which can be reduced the H+, which is actually as a product from the oxidation reaction to generate the H+, right, from the OER reaction. So H+ can be reduced to hydrogen. So hydrogen can be stored like as the energy from the sunlight. So as we compare the energy of the hydrogen and the methane, it's actually the advantage is the photometric energy density of hydrogen is quite high. Like even we can see the energy per mole is quite high of this methane compared with the hydrogen. However, the photometric energy of this hydrogen is quite high compared with the methane. So there's pointing out many works already done in this field. However, I would like to tell you some of them so the very major problems here. So first of all, if you see the high hydrogen absorption reaction rate is actually using CD material, CD-based material, right? And then we saw that CD-based material is quite toxic to the environment, and actually it's not so promising if we use for the large-scale application, right? And then the second one, usually we also use the co-catalyst with the PT. So we know that PT is a very high precious metal, right? The price is also very high. So that's why it's also very difficult if we want to scale up the application. Then the next one is the light source. Sorry. The light source. As you see, the light source, usually people use very high power, right? 300, 400, 500. So this actually release very much energy, and it's also a waste, right? And we also need a special cooling system during the reaction. Okay, so in order to solve this problem, then I will show you some promising catalytic, like this catalytic system, right? That we do not use the CD-based material or use the co-catalyst of PT, and also use a very low light source in the reaction. Okay, then to the next slide, you see for the water pollution. In the other hand, we also see the water pollution is also a very major problem to our life. Then you see from diagram, as you see, only 2.25% is fresh water, and this some of the fresh water is also contaminated, and it's a very urgent task for us to solve this problem also. Then some of the research will also try to solve this water waste treatment. So, for example, they use the traditional method like the physical, biological, and chemical treatment. However, they also create another problem like a secondary waste, and this also need to be handled later. So actually, we solve one problem and then we create the other problem and need to be solved later. And then the second thing is the high cost and limited lifetime application with the physical treatment, right? And finally, the biological treatment also give some problems with the toxicity of chemicals and large area for the application. Okay, then the further solution is we can use the advanced oxidation process by employing the hydroxyl radical. So hydroxyl radical can be formed during the photo reaction, right? Photo reaction, and this hydroxyl radical possess a very high oxidation potential, such as 2.8 volts, right? So that's why almost all of the organic material can be oxidized by using this hydroxyl radical. So as an illustration, so you can see this reaction. So as the hydroxyl radical attach the organic material, so you will form the alkyl group here. Then alkyl group will react with the oxygen to form alkyl peroxide. Then this alkyl peroxide is very active and attack the other organic molecules. Then finally, we form CO2 and H2O. Right. So that's why, because the same principle of the photocatalytic method, so energy and water problems, as I have discussed in this slide, can be simultaneously solved by photocatalytic process. So some general strategies can solve this problem, if we can see from this diagram, that we can apply even high bandgap materials. We can try to modify with solid solution photocatalyst, right? And then we can modify the surface of the catalyst in order to make the HBr effect. That's why we can have more electron concentration. And then we also can apply heterojunction PN heterojunction. Right? So this is what I'm going to discuss today. And then the last one that I have observed in some recent publication, that polymer supported photocatalysts also very promising, because it will hold the very tiny nanoparticles in order to make it reusable, right? Reusable. Okay. So the first part that I want to share to you is the GNOS photocatalyst for the application of HDR, hydrogen absorption reaction. So this catalyst is very simple. So let me show you the experimental procedure. I think this is very simple, right? So you just use the zinc acetate as a precursor, and then TAA as a sulfur source. And then we dissolve in 500 milliliter DI water. Then during the heating process until 95 degrees, then we add hydrogen as a reducing agent. Then finally, after 4 hours, we can see there's a white precipitation. Then this is what we call as the GNOS material. So actually, zinc will react with the sulfur from the TAA to form a zinc sulfide phase. However, because of the adding of hydrogen, then some of the zinc reduced and then become reactive with the oxygen. So that's why there are two kinds of anions in the one phase zinc sulfide base, right? And then to make this performance improve, we also try to add some precursors like cobalt, nickel, tin, lanthanum, Mn. So by very simple way, also during the process, we add this precursor. So of course, this process is done separately. Then we can have a different doped GNOS material, like shown in this figure. Okay. Then I just show you a very brief characterization for this GNOS-based material. So as we deal with different kinds of the metal, we see that the absorption, optical absorption also improves, right? So in this area, 250 until 350, the absorption light of the light is increased. Then if we see the SRD pattern, all of these SRD pattern show the same phase, like the same phase. It's only one phase. So if we compare with the commercial GNS, like we have three main peaks, and all the three main peaks actually tip to the right-hand side, indicating that the lattice parameter becomes smaller because the oxygen incorporated into the lattice, right? Except the last one, the top one. The top one here indicated we have the composite material, GNOS, with the gallium oxide, because we find out that we have this peak which is related or corresponding to gallium oxide. Okay, then we also briefly take the SEM and TM analysis. All the nanoparticle size is quite similar, like it's around 100 nanometer. And the very interesting result here is we can see from the SAED pattern, SAED pattern. So flatted electron diffraction pattern. Then the interesting thing here is the blood ring pattern, right? The blood ring pattern. So this blood ring pattern indicated that we have a solid solution formation. So if we try to analyze the inner circle, like in a circle, the radius is actually related with the JNS. Then the outer related with the JNO, right? So this ring pattern located between JNO and JNS, so indicating that it's already proof that we have a solid solution formation of oxy sulfide. So that's why we call this as JNOS. Okay, then we do the SER test, hydrogen absorption test. So this is a typical photo system for the hydrogen absorption test. So here is the reactor. So we throw in the argon, like at the first, and then we remove all the atmospheric gases. Then after that, we close the door and turn on the light. Then with a certain interval of time, we take the sample, of the gas and throw into the DC chromatography, and we can see the pit which is related with the hydrogen absorption reaction. Okay, then you'll see that the different kinds of the metal drop into the JNS will give you different hydrogen absorption amount. So the highest one is shown here with the cobalt drop, right? Cobalt drop and nickel drop. So this is a very promising metal, right? Nickel and cobalt. So as we see from the beginning, from the presentation, from the Professor Jaka and Dr. Luri, they also mentioned that nickel is very promising material. Even in the photocatalytic field, this material also very promising. Okay, so just show you a very interesting result from JNOS during the hydrogen absorption reaction. The color change during the reaction. As you see, when we pulse with the light of UV, then the color from white color change to dark color, right? Then if we stop the lighting, no UV, then it will change back to white color. So this is very interesting phenomena. So then we ask why this color change. So we find out what during the characterization, the color change because of the oxygen frequency. Right? So that's why based on this phenomena, we try to derive the equation, propose the equation. So by using the Fink-Kruger equation, so we have seen that as a defect, because this catalyst is prepared at a low temperature, so there should be a defect, right? So the defect is a toxic oxygen defect. So this will involve into the reaction and to form the oxygen frequency. So the oxygen frequency is, during the reaction become more and more. So that's why when the oxygen frequency form more and more, the color change become black color. And this oxygen frequency is very important, play a very important role in the reaction. So it will absorb the water molecules and then makes the reaction become easier, right? So water can be oxidized to form a proton, and then proton finally reduced again by photosynthetic electron to form hydrogen. Then we have proved that the reaction can be done in a pure water, without the host scavenger. But in this case, we try to make the efficiency become higher. So that's why we also add the host scavenger such as this ethanol. And ethanol will also improve more oxygen frequency side. So oxygen frequency, as the oxygen frequency side more and more, so it will have more absorption of the water molecule and make more proton, and finally can be reduced to hydrogen. Then the efficiency of the hydrogen absorption reaction become higher. Okay, so this is the kind of the specific setup in our lab for this hydrogen absorption reaction. Okay, then I'll show you some of publications related with the JNOS. We have published some of the papers related with this JNOS, and it can be used for hydrogenation reaction also. So the first one is the cobalt drop, as we have discussed in the previous slide with a very simple characterization that is, so we have a cobalt drop into the JNOS, and it shows that the hydrogen absorption reaction is quite high here. and also can be used to hydrogenate the nitrophenol to form aniline and azobenzene to form aniline. So this is very promising materials that we can do two kinds of applications together, like hydrogen absorption reaction and the chemical conversion. So this is very green process because we just use the light and the powder, and we add the chemical into the reactor. Then we have the product after the reaction, and also it can evolve the hydrogen during the reaction. And this is the kind of the proof that we can see from the UV visible that azobenzene change to aniline, and also for nitrophenol change to aniline during the reaction. Okay. And the next one is white dot JNOS. So when white dot into the JNOS, we'll also see that we can work for the hydrogenation reaction. So in this case, we only do the hydrogenation reaction to change the azobenzene to aniline. That you can see from this figure, the azobenzene actually is yellow color at the beginning, and after the reaction, it becomes yellow colorless. Right, means that we have the aniline product. So it also is shown with the UV visible peak at 298 nanometer. Okay, and then here we try another concept with the indium dot the GNOS. So this is I do not show in the characterization, but I think this is quite interesting to show you because indium hydroxide actually has a very wide band gap that actually is not active during the reaction. Right? So you see in the figure, the band gap is around 4.5. So basically, if we use the visible light, this material is not active. But however, when we drop the GNOS with the indium, then the band gap becomes smaller. Then we have the photoexcited electron. Then because the conduction band position and the indium hydroxide conduction band of the indium hydroxide is suitable for the electron transfer. So this can help for the to make the recombination rate between electron and hole can be reduced, right? So because of the electron move from one phase to another phase, because electron move from indium dot GNOS to another indium hydroxide phase. So once electron move to the other phase and whole still stay in the indium dot GNOS phase. So this will improve the separation, the touch separation, right? So because they have now they are in the different phase, so it's not the possibility to recombine and become lower. So that's the concept and very interesting for this work. So this work is used for hydrogen absorption reaction in a feasible like illumination. And then the next one, this is also I did not show in the characterization, but we have a core dot, the cerium gallium dot into the GNOS, and can be used for different kinds of chemical conversion. So this basically show the nitrobenzene and azobenzene like on the surface of the catalyst because of the oxygen frequency. After doping these two metals into the GNOS, the oxygen frequency among on the catalyst basically improve, right? Much improve. That's why because of this oxygen frequency, then some of the polar part of this molecule can attach on the surface, and this will increase the absorption. Of course, the reaction will be improved also. That's why it's very effective for the chemical reaction. Okay, then this very recent publication with the core dot principle also. So we dot the nickel and Mg, right? Nickel and magnesium dot into the GNOS. So we call this an MZ photocatalyst. So in this research, we try 4 kinds of applications together. Right? So the first application is the hydrogen absorption reaction. So it's also very promising to evolve the hydrogen, and then it also can use for hexavalent chromium reduction, right? For the second application, and then for the third application, we mix all the dye together, like Mg, Mo, and RSP, right? Because these three kinds of dye can represent cationic, anionic, and neutral dye, right? So some of the work just show the application on the cationic dye or anionic dye or just neutral dye. But in this case, we try to mix all together, and you will see that this is very interesting that all the pitch of this dye has been degraded right after the reaction. So you see the time is only 1.5 hours, right, under solar light illumination. So all the pitch for MB, MO, ISP, and MO all degraded. Then the last application is for the chemical conversion. We also find out that this can be used to hydrogen and azobenzene become aniline. As you see from this figure, the color of the azobenzene, of yellowish azobenzene, change become colorless, and so the pitch of the aniline come out during the UV visible spectroscopy analysis. Okay, then the second part that I want to show you is the PN heterojunction. PN heterojunction to reduce the toxic hexavalent chromium. So in this case, actually, this is the zinc sulfide base, zinc sulfide base material. We drop with the Ag and In metal and make the tank jet become lower. Then to make this material become more efficient, we couple with the T-type Ag2S, which has a lower band gap, and this can make the efficient electron transfer and hole transfer during the reaction. So first of all, I would like to show you a very simple filtration method. So this done in oleolamine solvent. So we just take all the necessary precursor for this AgINGNS. We take the Ag nitrate, indium chloride, zinc acetate dihydrate, and put into this oleolamine solution, and try to vacuum to clean the to make the air, atmospheric air, to pull out all the atmospheric air. Then after 120 degrees for 2 hours, then we try to inject the sulfur source. The sulfur source is actually dissolved in oleolamine first, oleolamine. Then we will form a very special color, like a black color. The red color is like a black color, and then we inject into the solution. Then we will form a brown color solution. Right. So after 220 for 1 hour, then we will form nanorods of ATN and GNS. And then we wash do the washing procedure, centrifuge, and get the powder. Then the next the next step is because we want to combine with the P-type of the Ag2S. Then we take the powder of AGI and GNS, just disperse in a solution. This DI water, DI water, and then we add Ag nitrate as a precursor. Then the next step is we add sulfur source by using sodium sulfide. Then after 10 hours, just stirring at room temperature to make it uniform. So we take 10 hours to make all the Ag2S formation attach on the surface. Then finally, we wash and clean the powder, the precipitation. Okay, then we try to analyze the powder with the SRD characterization. Then we see that all of these patterns actually basically show the major phase of GNS, GNS. Then with a very minor pitch of Ag2S. So we confirm that we form a formation of two phases, right? One is GNS phase, actually dot with the AgIN, and then the other one is Ag2S. And we try to prove that AgIN is already dropped into the lattice of GNS by using this SRD pattern. So we try to zoom in the very specific area of this pitch, right, at 220. So you see the pitch shift to the right-hand side, right, for the pure GNS, commercial GNS, while our materials is after dropping with the AgIN, then the pitch shifts, right? So it means there's a lattice parameter change because of the AgIN drop into the lattice. So then we also try to do the TM analysis, transmission electron microscopy. And we see that
excuse me, Dr. Hairus.
Yes.
Times five minutes remain.
Okay, I will do it. And you see that there is interface between the materials like Ag2S and AgNS. Yes, just to prove that we have the heterojunction formation, and this so with the SAED with the patterns that indicated the JNS phase and Ag2S phase. Okay, then just to show you the SPS analysis that we have all the elements, then also the element binding energy of each element in the PN heterojunction. So the next one is to show you the DRS after and before the use for photocatalytic reaction. And it seems like that there is the optical absorption is degraded because some of the chromium triplet is attached on the surface of the catalyst and make the optical absorption become decreased. Then here is the main experiment that we try to reduce the chromium 6 become chromium triplet. Chromium 6 is with the red color, right, with a specific agent, and we can see the color of the chromium 6+. And after the reaction, we form a chromium 3+, and so it's so with the green or colorless solution. And the best composition is 10% of Ag2S on AgI and JNS. So if we increase the performance, the percentage of the Ag2S also show the same performance. So it seems we have the optimized condition for 10% Ag2S. Then here also show the proof that after the photocatalytic reaction, we have a chromium peak shown in the EDS analysis. And the performance a little bit degraded because the surface of the catalyst is covered by the chromium triplet. And this is also show the proof that we, after the reaction we take for the SPS analysis, we also show the chromium triplet with a very specific binding energy. Okay, then this show the conduction band and valence band change when we go with the IN and AD become smaller. And after the formation of the heterojunction with the Ag2S, then electron can easily to transfer from conduction band of Ag2S to conduction band of the AgI and JNS. And similarly, the hole also transfers to the Ag2S, but then this makes the charge separation become better. And this is the proof for the oxygen formation after during the reaction. Yeah. So electron is used to reduce the chromium reduction, and hole is used for the water oxidation. Then the product is oxygen. Then find out that there is oxygen during the reaction. Okay, here finally I would like to conclude that GNOS-based material is very good for the hydrogen evaporation reaction and also for the chemical reaction by hydrogenation. And there are some advantages that I should mention here for the GNOS photocatalysis. Easy to prepare, low cost, no co-catalyst needed, such as PTAU, and then low power activation. So we just use only 16 watt UV light, so very low power, and then environmental friendly materials, abundance in chemical, reusable, and then we also use a very friendly host gas sensor such as ethanol. So we have seen that there are many reagents, toxic reagents used during the hydrogen evaporation reaction by other works. But in this case, we only use ethanol as very friendly, right, to the environment, and then also possible for the sunlight energy harvesting material. Then the next one is the strategy by forming the PN junction. Also, it's very promising, right? So we see that it suppresses the recombination rate and improves the charge transfer. That's why the efficiency is enhanced after that. Okay, that's all for today, and thank you very much. I'm welcome for the question QA session for this morning.
Okay, thank you, Dr. Hairus, for your nice presentation, very comprehensive and also interesting research. As I mentioned, the photocatalytic production of the hydrogens can be created from the water splitting process has gained attention now. And since it is very low cost, low energy consuming and environmentally friendly process. And finally, we comes to the last session of this guest lecture session, which is questions and answer. Take a look at the column chat. I found some questions already appears in the column chat, which is delivered by the first questions delivered by Pak Rizky Ginting with the questions regarding the photocatalytic conversion of the fatty acids to be biohydrocarbons. And this questions is toward to Dr. Hendra. And the questions is, what do you think, or what your opinions about the challenge of the development of photocatalytics to convert the fatty acids to be biohydrocarbons, compare with the common process like the carboxylation process to replace hydrodeoxygenation and hydrodecarboxylation and also oxidative decarboxylation. Dr. Hendra, maybe you have the already have the answer, so please.
Okay. Thank you, Bu Lucy. So thank you, Pak Rizky Romadona Ginting, for the question. So asking about the photocatalytic conversion of fatty acid to biohydrocarbon. Yeah. So as I mentioned before, so this research is actually commonly new, just published in 2020 in Nature Catalysis. I think the first author is from China, Wang et al. So in principle, the photocatalytic decarboxylations can be conducted under mild conditions. Yeah. So at ambient temperature and using also the hydrogens as the gases at 0.2 megapascal, yeah, or 20 bar. So the main challenge of this photocatalytic technology development is how we can actually develop non-noble metal catalyst. Yeah, because at the moment the catalyst that is actually give the highest yield and also selectivity is actually still under platinum dope on TiO2 photocatalyst. So the platinum is actually acting as a noble metal, which is actually very expensive, yeah, at the moment. But the consequences of using the non-noble metal catalyst, we have to make sure that this non-noble metal catalyst can effectively provide interactions between the catalyst and hydrogen, because as we know that in the photocatalytic decarboxylation process, so when the electron is already separated from the holes or negatively charged and also have separated from the positively charged, so the electrons is actually reduce the hydrogens into form of the hydrogen atom. So the hydrogens which can create the hydrogens rich surface on the catalyst, while on the valence band where there's actually a positively charged can react with the fatty acid. So the fatty acid will get oxidized and will remove the CO2 to form, we call it the alkyl radical. Yeah. So this alkyl radical and also the hydrogen's rich surface on the catalyst will actually react and to form the hydrocarbons or the alkane. So based on the result that is actually reported from the work, it is actually stated that the selectivity is already higher than 90%. And the most products that is actually generated is actually C17, so around 70 until 80%. Yeah. So yeah, our challenge is how we can actually develop cheaper catalysts, yeah, in order to conduct this kind of the simultaneous reactions, yeah, to provide the selective biohydrocarbon that we want to get from these reactions. I think that's my answer, Bu Lucy. Hopefully it answered the questions.
Okay, I think it was clear about the first questions. The answer is very clear. Maybe Pak Ginting, do you have some comments? No? Comments? No? Okay. Okay. Now we are going to the next questions from Miss Rizka, our Master of Ceremony today. Miss Rizka have two questions toward you. I think both Dr. Hendra also can answer, also Dr. Hairus. The first question is why the Langmuir-Henswood mechanism is generally preferred for photocatalysis instead of maybe other adsorption isotherm instead of Langmuir is Renwick also, and why this questions is generally preferred for photocatalysis. And the second question is why some photocatalysis are unable to degrade some pollutants in photocatalysis process. So maybe at first, Dr. Hairus.
Okay, thank you very much for the questions from Ms. Rizka Lestari. I think why the RH mechanism is preferred in the photocatalysis reaction. So this, as I observed from the some papers, this because of the absorption at the same site. So when the photocatalytic reaction happens, so the first step is actually the absorption. So without absorption, the species or chemical species cannot be degraded because there is no touch transfer. So in this case, the site of the photocatalysis for the absorption and the reaction site the same place, right? So there is a rate determining step during this because the catalyst should be absorbed first, and then after that we have the reaction, then it will detach from the surface of the catalyst. So that's why you will follow like RH mechanism. And also during the photocatalytic reaction, usually the temperature is quite stable, right? Quite stable. We just we use the water cooling, like water cooling system during the reaction. That's why I think it will prefer the RH mechanism. So that's the first one. And then for the second one, why some photocatalysts are unable to degrade some pollutants of the photocatalytic process. So based on my experience, some catalyst is very active with a very specific dye. So this is because of the property of the catalyst itself. So for example, some catalysts can very actively generate the electron, and the electron can reduce the oxygen to form oxygen radical. So this oxygen radical is very specific, also can reduce a specific dye, right? But in the other side for the hole sometimes is not too much active. Maybe it's trapped on the surface of the catalyst, or there are so many factors like on the during the catalytic reaction. So hole become not effective, and electron become effective. That's why we make the oxygen radical become more than the whole reaction. So that's why it's very specific for the reaction. And sometimes the hole is very reactive, and electron is trapped by somewhere in the catalytic site. Then hole can be also oxidize the specific dye. So that's why I think it's related with the generated radical, like on the surface of the catalyst. I think this is my answer for the second question. That's all, Dr. Lucy.
Okay, well answer, I think. But maybe from Dr. Hendra have another opinions from your side regarding these two questions.
Yeah, I think the same questions, yeah, especially for the mechanism of the Langmuir-Henswood, yeah, because commonly for the reaction for the photocatalysis commonly occurred on the surface of the photocatalyst, yeah. So it's actually need for the reactants that is actually adsorbed first on the surface of the photocatalyst, and especially for the wastewater treatment, we need the oxygens, yeah, as the carrier gas to perform or to create the radicals. We call it the reactive oxygen species, yeah, consisting of the superoxide radicals, hydroxyl radicals, and peroxo radicals, and so on. So this reactions actually occurs when these two specific reactants is actually adsorbed on the surface first. Yeah. So that's why, the researchers can be concluded that the most suitable mechanism for photocatalysis processes is based on the Lang-Mariense-Wood mechanism.
Questions, Dr. Hendra. What do you think about why some photocatalysts are enables to degrade some pollutants in photocatalysis process? For example, maybe the questions can be like this. So, for example, we mix the artificial waste from dye pollutants, and we exactly don't understand the properties or the physical characteristic of these dye pollutants. So some kind like trial and error. We use anything of dye pollutants, organic pollutant. I mean dye pollutants, and how we make sure that our photocatalysis will be suitable to remove these dye pollutants.
Okay, so I think going back to the fundamental aspects of the photocatalyst, yeah. So we know that the photocatalyst has a certain band gap, yeah. So the positions of the conduction band and the valence band is actually become our main considerations, yeah. So the positions of the conduction band must be higher than the standard potential reductions to create the radicals in these cases, yeah. So once the conduction band, so in the conduction bands, the electrons will actually be consumed with the oxygens to create the superoxide radicals, yeah. So these standard potential reductions of the oxygen reductions to create superoxide radicals must be lower than the conduction band potentials of the photocatalyst, yeah, in order to make sure that this reactions is occurs, yeah. And same thing with the valence band. So the valence band positions must be lower than the positions of the standard potential reductions to create the hydroxy radicals from the oxidations of the water, yeah. So if these two requirements has been actually fulfilled, I can actually certainly believe that this photocatalyst can actually destroy all of the organic pollutants, because once the radicals is actually generated or created, yeah, in our system, in our photocatalyst, yeah. So the radicals is actually very reactive, yeah. So whenever whatever organic pollutants is actually occurred or presence in the system, it will actually spontaneously attack, yeah. The radical is spontaneously attack the organic pollutants, and it will actually degrade to form the simple or the more simple compounds, yeah. I think that is actually my answer for these problems.
Okay, I think it's mind-blowing for me. Okay, the others questions is in the case of the common or in general, we mix the artificial waste using single dye. For example, we mix the artificial dye pollutants using rhodamin B only, and we degrade with the photocatalyst, some photocatalyst. But did you ever has the research that use mixed dye? For example, rhodamin B, you mix with the methyl orange or methylene blue. So mix the multiple dye in the one's batch of reactor, and you use photocatalyst to degrade these pollutants. Did you ever did this research? I think I still cannot find where is the research, the current research that work with the multiple dye, but degrades with the certain photocatalyst. I cannot find that, but maybe from your experience, you already did this research.
Is it for my questions? So I need to answer. Okay. Okay, so actually I never using the mix always. Yeah, why? Because we need to evaluate. Yeah, so we need to evaluate the proper or the performance of our photocatalyst. Yeah, so if we use the mix, so it is actually possible to do it. Yeah, so when we have methylene blue and methyl orange and mix it together, but we need to evaluate the reductions of the concentrations of both ways, yeah, during the photocatalytic activity, yeah. But in order to make it simple, usually the researchers, yeah, decided to use just a single model compounds, yeah, because yeah, again, we need to evaluate our photocatalytic performance, so just better to use the model compound. But for, yeah, I know that for larger applications, so I believe that the waste is actually much more complex. It's not actually containing only one model compounds, yeah. For instance, the textile wastewater, I believe that instead of just the dye, there is actually a lot of contaminants, yeah, maybe solids, particles, and so on, yeah. But again, this is actually the aim of using just a single model compound just to evaluate our photocatalytic performance, yeah, I guess.
Okay, thank you for the answer. So maybe
Maybe
from
Pak Hairus have another comments.
yeah, Dr. Hairus have another comment.
Okay, there's a very interesting question for the real dye degradation. So it's very, I have tried this before with the nickel and Mg.2 GNOS catalyst. Maybe I would like to share my screen again. So you see from this claim, I have four kinds of applications for this nickel and Mg.GNOS. And then you see, I tried these materials for the Mb, RHP, and MO, 3 dye together. And after we mix these 3 dye together, you see the color of the dye is around purple color, right? But a little bit light color. Then after 90 minutes reaction, then all the peaks of this MO, MB, RHP all degraded, and it's very interesting. That become a small. I think this not because we do not do a further characterization after the reaction for the reaction solution. So we see from the UV visible the maybe a small molecule spot here, but the main RHB, NO, and NB dye already degraded. Then it become a colorless solution. But because there are too many words in this paper, so we just decide that the word is just stopped until here, and we just show that this material is possible to have can generate the hydrogen also for environmental remediation. I think maybe this is because of the active radical of superoxide and hydroxide is very balanced for this material. Then that's why even we use different kinds of dye, such as cationic dye or anionic dye or neutral dye, they can all be degraded at the same time. I think this is my answer for Dr. Lucy.
Yeah, I think I have also one additional point, maybe. I have also done other type of the waste industry, like the pharmaceutical industry, such as carbamazepine, sulfomethoxazole, which is actually very complex. But we have actually proved that the concentration is actually degraded during the photocatalytic reaction. But it is actually very important to know what is actually the derivative products that is actually generated after the photocatalytic reactions. So that's why the advanced characterizations using, for instance, the LCMS, liquid chromatography, mass spectroscopy, I think it is actually needed to find out whether the final products that is actually generated after the photocatalytic degradation process, for instance, is much more safe, because we want to, at the end, we want to make sure that when we throw this waste into the environment, we have to make sure that it is actually safe. So that's why the toxicity of the final products and also other things that we need to consider is actually we have to make sure about that. Even though from the UV vis, there is no reactants, or for instance, the carbamazepine or sulfometaxazole also is actually found. But when I did the LCMS, there is actually still a complex products still actually obtained. Yeah, but yeah, this is actually our concern. Yeah, about this. Yeah, so we have to make sure the final product is actually more safe and also more not more non-toxic, yeah, compared with our reactants. Yeah.
Yes, I absolutely agree with the Dr. Hendra. So that's why we need to actually do the further characterization using the LC, SCGC instruments. So sometimes the degraded product become more toxic than the parent product. So I think this is become our concern also. So the further characterization is very important.
Yeah.
Okay.
Okay. Wondering about the removing of organic pollutant from the water. And so far in my research, I still use the artificial waste using dye, but not yet try to use like oil waste using photocatalysis. And what do you think, both Dr. Hendra and Dr. Hairus, which one is better, using absorption process or using photocatalyst to degrade the crude oil from the water, from your side? Which one is better?
Okay, I think of course we do not want to generate another kind of the solid waste after the reaction, after the degradation. So if we use the absorption, we will generate the second waste. So this should be solved later. So actually we just solve one problem and generate the other problem. So I think the photocatalytic method is quite promising in order to make to degrade this organic pollutants. So in my field, I think photocatalytic reaction is very promising to degrade the organic dye. That's all for me.
Yeah, I strongly agree. Yeah, with Pak Hairus. I think the adsorptions actually can create another problems. Yeah. And the absorption sometimes the adsorbent sometimes is not actually stable, and it is actually easy to be saturated as well. Yeah. It's not actually acting as the catalyst that is actually used, so we can actually recycle the catalyst until different a lot of cycles. Yeah, depends on the reactants that can make the catalyst become denaturated or destroyed. Yeah. But I think the lifetime of the catalyst is much more promising compared with the adsorbents. Yeah, and also again, it's not actually create another problems where, because the pollutants, organic pollutants, can be safely degraded to form our final product is CO2 and water.
Yes. So the other problem is actually sorry. Yeah. I just want to add some points to for this degradation. So when we decrease the size of the particles, then the surface area become increased, then the efficiency of the reaction also increase. And the problem when we decrease the particle size is sometimes the mobility of the nanoparticles become very fast, and it just reach out to the environment, and this make another problem for human health. So that's why I think that's also possible if we can make a polymer substrate and then hold all the nanoparticles on the surface. Then this polymer substrate and become very useful for the usability, as mentioned by Dr. Hendra, that usability is very, very important. So in order to make the not nanoparticle reach out to the environment, this substrate, as for example, we use the nylons or some polymers that then hold the nanoparticles not to be reached out. This is a quite important strategy, I think. So I have actually ever done this before with the nylon. Then, but we compare with the nanoparticles from efficiency. The efficiency of the degradation is quite low, much lower. So maybe it's like 20% only from if we compare with the nanoparticles. But this can be reused very easy to be reused because it's like a membrane, and then we just immerse into the wastewater and illuminate with the light. After that, the solution becomes clean, and we just remove the membrane out, and then we can just do the next reaction, and this can be repeated until 5 times, 6 times, and very efficient, I think. Okay, there's all.
Yeah, or maybe another way is actually to integrate these two technologies. I think is promising as well. Yeah, so integrating adsorptions and also photocatalytic technology. I think a lot of papers have already reported about integrations about these two technologies. I think it's promising as well. Yeah.
Okay, so I think there are some questions from Bu Mutia Reza. So this questions is toward to Dr. Hendra. The questions is about the comparison of the titanium dioxide and anatase with the others titanium dioxides, rutil and brochite, and why titanium dioxide anatase is the most active crystal base.
Okay, so maybe I'll try to answer this question. So it is actually reported that the TiO2 anatase has a better charge carrier mobility, yeah, compared with the rutile. And yeah, if we're comparing the band gap of the anatase is actually higher, yeah, 3.2 electron volt, and rutile is around 3 electron volt. So that's why the researchers try to find the optimum mixtures between these two crystal phases. Yeah, so they try to mix which one is actually the optimum ratio. So that's why now in the commercially available, yeah, it's not actually just a single crystal phases that is actually sold, yeah, which actually just is now actually a mixture. So we call it the P25 degussa or air oxide. So which consisting of around 80% of anatase and 20% of the rutile, because from the rutile we have an advantageous has lower band gap, yeah, while for the anatase has better charge carrier mobility, yeah. So that's why in here try to integrate these two advantages from each crystal phases to make it stronger performance.
Okay, maybe from Bu Mutia has some comments. No, so this is my last questions. From some cases, I mean certain cases, the use of the catalyst, sometimes we need to consider about the pH, pH value, in order to to evaluate the effect of the pH value, and also the thermodynamics properties, which is included in the phenomena of the photocatalysis process. So so far, what do you think about the photocatalyst that we use for pharmaceuticals waste? If we still use to evaluate the pH and then also the thermodynamic properties, is it necessary to evaluate these parameters?
Yeah, I think from my perspective, well, it depends on the reactants, yeah, that we want to actually degrade. Yeah. So for instance, we evaluate first what kind of the properties of the reactants, whether it's actually in the acid pH, neutral pH, or maybe in the basic pH. Yeah. So we can actually tune in later on the reaction medium. Yeah. So it sometimes it actually consisting of two different perspectives. Yeah, we can actually tune also the medium of the reactions, or we can actually tune the basicity or acidity of the catalyst. Yeah, so the basicity of the acidity of the catalyst can be also characterized actually, yeah, using, for instance, the temperature perogram desorptions, yeah, TPD. We can actually use carbon dioxide TPD or ammonia TPD to find out the basicity and also the acidity of the acidity sites of the catalyst that is actually present in the system. Yeah. And yeah, again, we can also tune in the reaction medium. Yeah. So during the photocatalytic performance evaluations. So we can actually tune also the reaction medium, whether we can tune into the acidic, neutral, or basic pH, and still depends. Yeah, again, it actually depends on the reactant or the waste that we want to degrade. Yeah, in these cases.
Yeah, I got it. From Dr. Hairus, do you have any opinions?
Okay, thank you. I think I agree with Dr. Hendra, because different pH will give different transfer from the catalyst. So we need to tune the pH. So that's why some papers also try to make a different pH for one work and try to find the maximum pH in this case. And then about the temperature for the reaction, I think if we increase the temperature, the catalytic activity becomes decreased easily. So that's why I think this is just based on my experience. That's why we need the cooling water or some cooling system to make the temperature of the system stable, because we don't want this kind of temperature affect our catalytic reaction. I think that way. Okay.
That's a prompt answer, and I think it's clear. Actually, I have some questions for Dr. Ruri and Prof. Jaka related with the photocathodes for the fuel cells. But unfortunately, Prof. Jaka has another conference today. He has to deliver some presentation also in others agenda. And also Dr. Ruri also has the other agenda in the same times. Things with his leaders to give the opening remarks and welcoming speech in graduation in ITS. So probably I will deliver my questions to them in outside of this forum. So finally, we come to the last session of this guest lecture sessions. And I would like to thanks to our honorable speakers, Dr. Hendra, Dr. Hairus, Dr. Ruri, and Prof. Jaka that give us their experience, and then also the presentation, which is very informative and useful. And also, I would like to thank you to all the audience for the participation in today's meeting. Hopefully, all the material presentation is useful for all of us. And thank you for the attention. We will back to the Master of Ceremony, Ms. Rizka. Thank you very much.
Yeah, thank you, Dr. Lucy. And thank you for once again for all of guest speaker, and thank you everyone. We moving for giving appreciation to special guests and guest speakers. We will display the certificate. Please, Mr. Bagus. Please slideshow. Okay. And the first one, certificate for Professor Jaka Sunarso as our special partner of world-class professor. And then we move on to the next certificate for Dr. Ruri Agung from Institut Teknologi 10 November. And then the next one is certificate for Dr. Wibawa Hendra from Institut Teknologi Bandung. And the last certificate is for Dr. Hairus Abdullah from Universitas Prima Indonesia. Okay, thank you, Mr. Bagus. Then we come to the end of the event. Forgive us if there are many shortcomings in this event. Finally, see you at the next program of World Class Professor. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon.
Good afternoon. Thank you very much for
Dr. Hendra.
Lucy. Thank you.
Yeah.
Good afternoon, everyone.
Good afternoon. See ya.